Welcome everybody to the day 2 of our Cybersecurity Fundamentals Bootcamp. My name is Chris Johnson. I'm the Chief Operating Officer here at GoCloud Careers, joined by Mike Gibbs.
Welcome everyone.
Our founder and CEO. And just so you know, if you happen to join with a bot or anything like that, you will be removed. We do not allow any automated note takings or AI interfaces to interact with us. So, in case you get an email or something saying that you were removed, it's your bot. So anything like fireflies, Otter, all those other things. So while we're waiting, we're going to get started here in a minute or two. But while we're waiting, let us know where you're from in the chat box. I am here in St. Petersburg, Florida.
I'm in Port St. Lucie, Florida. Bronx, New York. Spent a lot of time there. Romania. Wow, love that. Toronto. New York. Worked there for years. UK, South America, Algeria. Love that. Berlin, Hoboken. Worked over there too. Nairobi, Kenya. Fantastic. Houston. DMV. Where's DMV? Calgary?
DC.
Okay, gotcha. Thanks. Charlotte, Chicago. Love this. Brussels, Belgium. Spent some time there. Tunisia, wonderful. We have a student from Tunisia doing really well in the enterprise architect world. Ghana, love that. Turkey, Istanbul, I know that part of the world extremely well. Spent lots of time there. It's beautiful. London, Paso, South Africa, like Tyrone on our team. It's fantastic. Germany. It's terrific.
All right. Well, before I let Mike get started here, just a few housekeeping notes. So this is a live training session. And so with that in mind, we're going to be, we don't have specific start and stop times. We're going to be kind of following a natural flow. So what we're going to be doing is we're going to have Mike lecture, I guess you would say, for, I don't like that word. I don't like lecture. We're going to let Mike share with us for, 15, 20, 30 minutes, depending on whatever the current discussion point allows for. And then we'll stop, take questions for a little bit, and then we'll get back to the content and go again 15, 20, 30 minutes, whatever it might be. And then we'll do questions again. So we'll follow that pattern throughout the day. And that's how we're going to go. Now, keep in mind, we only have a limited amount of time, so we are going to be capturing questions as they come in the chat box and keeping track of them so that we can answer them when we get to the questions and answer section. Now, if we tend to get a high volume of questions, we may not be able to answer all the questions. But because we are keeping track of them, we're keeping track and are going to be creating a question and answer portal, repository, I guess you would say. Last week we did a good job of getting all the questions addressed. So that's that. But we are keeping track of them just in the event that we happen not to get through all of them. So that's how we're going to be doing it. We're going to try and keep any questions that we have, we're going to try and keep them on topic. So as much as we love to answer career-related questions and architect career-related questions, that's not what we're going to be doing here. But we'll be doing that tomorrow at 3 o'clock. And we'll be putting a link in the chat box there for you for that Security Architect Career webinar where you can ask career questions. But today we're going to be taking questions as it relates to the material that we're going to be going over for the cybersecurity fundamentals. Also, I'm going to encourage Mike that if we get a question that's related to something that we might be covering in the next section or in the near future, I'm going to suggest that he hold off on answering the question until we get to that topic. Again, because if we're going to be covering it in 30 minutes, uh, let's wait until we cover it in 30 minutes, or wait until we cover it in an hour. That way, again, just trying to keep that continuity, because sometimes people's brains start to connect the dots, and they're already getting ahead of us, which is great. But we want to make sure we stay on task. So those are my housekeeping points for you. So in addition to myself and Mike, we also have Tyrone, Leo, and Alonzo here as well from the Go Cloud Careers team. So you're going to see each of them are like me. They're going to have Go Cloud at the back of their name. So just in case you happen to need something or want to send something to someone from our team directly, that way you know who to who we are. So that is that's all I've got. Oh, we got Noel in Tampa. Hey, nice to see you, neighbor. I'm in St. Petersburg. So anyway, that's all I've got. Who is ready to get on with the training? Let me know in the chat box. Uh, Mike, I think you're ready.
I am all kinds of ready.
All right. Sorry, everybody. One last bit of housekeeping that I want to make sure everybody keeps in mind. I say this before every training that I'm a part of is this is like any other material that you're going to be learning. You may not get it the first time. So keep that in mind. We're recording this so that we can share it with you so that you can review it again and again. But with that in mind, also take notes, write down things that you might not be familiar with. Use your notepad. I got my notepad around here somewhere. I can't find it. Use the notepad on your desktop. Keep track of stuff. Come back and watch it again. Write down a timestamp of something that might have been covered, and you're like, okay, I want to come back and watch that again. It's an iterative process. You're going to probably have to watch things a few times. You may have to read a few times, write things down. So keep that in mind. I always like to share that with everybody because I know sometimes people have this expectation that they're supposed to get it the first time. No, I don't know. I don't know anybody that gets something the first time, let alone something as
Like
complicated
this.
as cybersecurity or networking or anything like this. So just keep that in mind. Set that expectation for yourself. Give yourself the grace to know, okay, I'm gonna have to come back and watch this, or I'm gonna have to come back and read it, and I'll get it. But I may not get it the first time. And if you're looking for the recording of day one, the recording for day one is on our YouTube channel. It is featured on our YouTube channel. Uday just put it there in the chat box for us. Oh, and he just put it to the timestamp that skips me talking at the beginning and goes right to where Mike starts teaching. Thank you, Uday. So um, that's where your recording will be. So that's what we've got. I just wanted to get that bit about don't expect to know it all at the beginning. I just want to make sure you guys have that proper expectation for yourselves so that you don't get discouraged or disappointed that you don't grasp what subnetting or BGP or firewalls or load balancers or any of that stuff is, because I certainly didn't get it the first time. So that was what I had, Mike. Now I will let you get into laying the foundation of the network before we start talking about how they attack the network.
So today we're going to talk about network security. And I thought about this very deeply because every time you teach a CISSP bootcamp, for example, they teach about all these types of network attacks, but then they don't explain what the actual network is, how the actual network works, and you could never understand how these attacks occur. So I want to do it two ways. The first thing I want to do is introduce basic networking and talk about how the routers work, the switches work, the wireless access points work, for example. And then when we talk about that, I'll show you the strengths and weaknesses and potential hacks. And then we're going to talk about the actual attacks. And then you'll truly understand it. Because when you truly understand the attack, it's pretty easy to prevent against the attack. But if you don't understand the system, the way the system works, what happens when you change one part of the system to the other part of the system, doesn't matter what you configure, it won't make a difference. What is a network? Seriously, think about what is it? Well, if you think about it, and I could tell you it's an interconnected series of devices, but what the heck does that mean? Well, let me show you what a network is, how a network moves traffic, and we'll cover some of the main elements along the way. So we're going to first start with three types of devices. And I'm going to use three types of devices, even though one of these types of devices doesn't generally exist anymore, because it sort of does in another environment. So let's have some fun with these three. So the first thing that I want to introduce is the concept of a hub. And I'll show you why. We're going to talk about this ancient piece of history, because we still use something like it. It's called wireless. But let me show you the way hubs, used to work, because they're, and then I'm going to talk about how these devices are actually connected together, what makes up a network. But I want to go over the three types of devices. So this is called a hub. And basically what you had in the back of this was just a set of wires so that everything that was plugged into this port could be seen by this port and by this port and by this port. This is what we used to use like 20 years ago. So if we have, and there's a reason, we have to work on these assumptions for many reasons. So if we got Joey over here and Nikolaus over here, if Joey wanted to talk to Maria, Nikolaus was still going to see it. Now, we can use cryptography to mitigate those things, but this was the basis of a hub. The other thing that I want you to understand is the way these worked is, because it's only one set of wires over there, imagine what would happen if this device and this device spoke at the same time. Electrically, it wouldn't work. So this device had to speak at a different time than any of these devices. If any of them all decided to speak at the same time, they all had to stop transmitting, because we only had one wire and potentially 10 computers in there. From an architecture perspective, of the only time you can speak is when nobody else speaks. How well do you think that's going to scale? Not real well. Two people in a room. Sometimes the other person doesn't know when someone's finished speaking and they start speaking too, and they collide. Now, imagine being in a restaurant with 30 people in it. Is there ever a time where not anybody's speaking? No. So what happens is every time somebody or something speaks, they all collide, they all back off, and the computers had a little random back off timer. So Leo's timer would be 1 millisecond, and mine would be 3 milliseconds. And hopefully, if we both transmitted, we didn't collide with our data. That's the way these hubs used to work. So why am I showing you something so ridiculous? Well, in today's world, we still have an environment where this works exactly the same way. And this is a wireless access point. So what happens is all of your little PCs or iPhones that are connected are all connected into a wireless access point, and everyone's traffic can interact with everyone else's. It's the same problem as a hub. So if this thing is good for 2 gigabit a second, but 3 of these transmit at the same time, it doesn't matter how much traffic. So we never know how much traffic is going to get through in any type of environment like a hub, because it's all based on who's speaking, when they're speaking, why they're speaking, and when they're not speaking. Keep that in the back of your mind. So that is the way a hub works. So imagine if you just wanted to inject a whole lot of bad traffic at all times. Wouldn't that be a DDoS attack? Wouldn't that take the entire network down? It would take the entire system down. So clearly, that was a pretty terrible system, but we don't have a much better choice for wireless yet. So what we did is we moved into something called a switch, and I'll show you what a switch does. And it was the coolest thing. Heck, you know what? Let me grab a switch for you at the same time. So picked up an enterprise switch. Looks like a pizza box for a 48 port switch like this. And here's the way a switch works out of the box. If the traffic goes in this port, for example, I'm plugged into here. If I have unknown traffic, what will occur is it will flood out every port on the switch. Then when the person responds, I will know where the person is, and it will go between my port and their port. I'll map it out because it looks kind of ugly, me trying to hold up a switch. And Professor Cindy, are you going to be teaching today? Because you're more than welcome to. So let's build it out a virtual version of this. So now we have a box. In this box, we have a bunch of ports. We're going to piece these together when we start talking about different kinds of attacks. So here's our switch. So what we do is we have, so let's say we have Cindy's PC. Cindy's my cat. If you don't know Cindy, most people know Cindy. So we have little Cindy over here, and Cindy wants to access another computer that's sitting on side of the same local area network. Now, Cindy's got a friend called Sunny. Sunny is a beautiful Maine Coon, and they want to exchange information about their favorite kinds of tuna, and they're both plugged into the same network. So we're only talking layer 2 right now, and I'll show the differences between layer 2 and layer 3 in a minute in networking, but this is at the MAC address level. Here's what happens. When Cindy begins to speak, Cindy says, hey, basically, who has the MAC address for the Maine Coon? Sunny over here. And then Sunny responds and says, I own that MAC address. And future communication occurs only between Cindy and Sunny the Maine Coon. So what happens here is the switch builds a table of where to send traffic out of. So if Cindy knows to use this port to reach Sunny the Maine Coon, what happens if Caddy plugs into the network and Caddy pretends to use the same MAC address as Sunny? Where is the switch going to send its traffic? Which port? Maybe seen by Caddy instead of Sunny, which is obviously a problem. What happens if a hacker were to basically poison the table that determines where the users are on which port? And the switch keeps flooding data around and around and around and around and around. It gets multiplied out over the port. Do you see how you could take a network down like that? So there's a reason we're showing some of these things. So that is a switch. Let's talk about one additional concept on a switch while we're at it. If we put these, we can create virtual switches, and that's what's called the VLAN. And what that realistically means is we create an environment where we tell the switch, all of these ports, you're allowed to speak to each other. Now, we may have a whole set of additional ports on this switch that we don't want to be able to speak to these, and they won't be able to natively, because if these are in one virtual LAN, well, if these ports are in this one virtual LAN and these ports are in a second virtual LAN, if there's no router between them, they won't be able to communicate with each other. Which means we can add a whole heck of a lot of security real quick. It's a network when we own it. We have much less in this in the cloud computing provider. And then we have other devices called routers. So routers forward traffic from one subnet to another. So what these routers do is they build a map.
And Mike, we're not seeing anything if you're sharing.
Thanks, Chris. So what we do is if we have routers, what they do is they check your traffic from one network to another. And when we're talking network, it means a different subnet. So what this means is if you're here and you're the host and you're on a private subnet, say 192.168.1.0/24, which is what most of your routers are pre-configured to use when you typically get them from a what do you call it? For a typical consumer grade router that we get at like a Best Buy. So if your host is .2 and your host wants to reach something that's off its subnet, it can't do it by itself. So the host has to send it to this network device called the router. And let's say this is the IP address that we're looking for. We'll use Google's DNS address. Since these are Google's DNS servers, everybody knows them. They're Anycast throughout the internet. So let's pick something like that. If 192.168.1.2/24 wants to be able to reach 8.8.8, it has to look at its routing table. And if it doesn't have a router in its routing table to reach it, it can't. So what happens is the routers your host is connected to the router, which has to be on its subnet. So the host will send a message to the router. Do you have a route to it? And if the router doesn't have a route to it, it will drop the packet right then and there. And if the router has a route that gets closer to this, the router will look in its routing table and say, I have a path of it, and it will send it out this interface. And this router will look in its routing table, and if it has a path to it, it'll send it. And if it doesn't have a path with it, it'll drop it. And each one of these routers will do the same thing going back and forth. Did you pick up on one thing that I said multiple times? It is a big security connection there. What happens when a router, and they put the answer in the chat box, gets a packet and it doesn't have a route to the destination? What does it do with it? It drops the packet. So if traffic is sent to a router and the router doesn't know how to reach it, it gets dropped. Can you hack something you can't reach? You can't hack anything you can't reach. So there's going to be so many things that we're going to do on the network to make sure you can't reach certain things. So that's what we're kind of looking like. So a router basically has to build a map of every destination that's possible in some way, shape, or form. And that's how it knows how to go from point A to point B. It's the quality of that map. And the internet is designed now, UDI, to drop the packet and then send ICMP, Internet Control Protocol, that says, by the way, destination unreachable, instead of sending all the data back and burdening the networks. But so what does this really mean? What does the internet really look like? How does this work large scale? So first I'll show you in an enterprise, and then I'll show you on the internet. And I think that'll help it be really clear when we kind of put the pieces together. So what'll happen in your enterprise is you're going to have this. You're going to have routers that are going to do this. They're going to connect you, say, to your remote location. So let's say this is a global multinational environment, and it's a headquarters. So lots of companies have now moved their headquarters to Miami for various reasons. So they've got a new giant headquarters in Miami. So this is the corporate headquarters. Now, what you'll see is the headquarters probably has its own data center, or it uses a cloud provider, or usually most likely a combination of both. And this headquarters will probably need to connect to, say, 1,000 remote offices inside the United States and across the globe. So these organizations are going to have wide area networking gear, which are going to be routers, and they're going to have wires that they pay for from the phone companies to be able to reach the environments, not on the internet, prepaid cabling. And that's going to be private line. So this is what you call intranet, because it's going to the customer stuff, not on the internet, private. Private wires, if you will, in many cases, or if not, private encrypted connections. And they'll have multiple routers, and they may have, to be fair, they may have about 5,000 of these to 10,000 of these. Now, please understand, this will never be on the same service provider as this. Nobody's crazy enough to, like some people would do in a cloud, where they put all their bags in a basket and wonder why the cloud crashes and they're down. This always in history, we've learned the past. So if this is Verizon, this is AT&T. If this is Vodafone, this is Orange. If this is BT going to, say, Dubai, this is a Titsalot or something like that. So you're always going to have more than one, because we constantly have to have real things. Now, this headquarters will also have internet connections, and obviously that's going to be going out to the public internet. But these will also be routers that are going to connect to these things. And they'll be connecting to the public internet, which is not safe, not trusted. So all that will have to be encrypted. Then inside these organizations, what they're going to do is they're going to have very high speed routers. They're typically called layer 3 switches, but they are going to become the backbone of the campus. And what's going on here is these systems forward the traffic from point A to point B at a very high rate of speed. And they're designed to be highly available, higher redundant. They'll have multiple power supplies going to these things, multiple redundant cards, redundant cabling, redundant everything, redundant circuits that'll be going on. And of course, they'll probably have 20 or 30 links to each other and say link aggregation groups going this way. They'll have multiple link aggregation groups going this way. They'll have multiple link aggregation growing groups going this way. So that they could be like 800 gig links bundled and multiple of them bundled. We'll have them going this way because the only thing we're paying for, because it's in our campus, is lasers and fiber optic cables. So it's not going to cost that much for these cables. And we're going to make sure that we've got a lot of redundancy. Now, these will be layer 3 links, not layer 2. We can't deal with spanning tree for these kind of things. And then what will happen is we'll have another series of switches for the most part. Depending upon the size of the company, it'll be 2 to 3 layers of these switches routers. And what'll plug into the switches will be things like servers and things like your users. So what'll get plugged into the switches will be end devices. Now you'll also have storage boxes in these things that are going to be RAID arrays filled to thing, block storage, objects, file storage, and they're all going to plug into the network. So do you see anything here that becomes absolutely critical to availability? One thing I just showed you can break and everything could just fall apart. What's the weakness? What's the one mistake people can make? What's the one weakness? Okay. If you don't see it, I'll show it to you. Even if the firewalls
Are you looking at the chat box?
Yep, I'm looking at the chat box.
Okay, so let us know if any of them are right or wrong.
None of them are correct yet. So I'll walk you through it. So let's go back to this situation where we have a perfect high availability situation. Let's go back here. 2 power companies coming in, all these things, as I mentioned, redundant power, redundant this. How do the routers calculate how to go from point A to point B? It's the routing protocols. It's this OSPF domain inside of here. If the routers, for some reason, Billy Bob puts a bad static route in and redistributes it, a hacker puts a bad route into the system, and none of the traffic knows how to get from point A to point B, nothing works. I promise you, half of the big outages you've seen are related to someone that's got the routing wrong. Like the big Facebook outage, the big Google Cloud outage, the big Cloudflare in India outage. And that's just a few that people are willing to admit. I've seen these outages for decades and I spent my life cleaning them up. And it's usually because someone didn't understand IP addressing or routing. And that's what we do as network architects. But that's what I want you to see there. If this routing gets messed up, you've got absolutely zero. Because if your traffic can't go to point A and point B, it doesn't matter how good your links are. Anybody seeing where this is going yet? So this is what the internet looks like. And I'm sure you've experienced this. So the internet is a collection of, say, internet service providers. So ISP1, ISP2, ISP3, and ISP4. Now, these are all four separate companies. Now, let's make them fully meshed. So far, well, I'll draw some lines to make them fully meshed as well. And you've seen this in your life. You just may not know it. So let's say you've got a very large internet service provider, and they have BGP peering sessions all over the world. And then this very large internet service provider makes a BGP error. And all of these providers that actually do have a preferred path for it think ISP2 is the path, and they all send all their traffic through ISP2, and it never gets there because there's a problem in the internet routing. Somebody made a BGP error. This stuff happens all the time. So, depending upon how good your network architects are at filtering what routes are allowed in and what routes are allowed out and authenticating peers and getting things, this is one of the bigger weaknesses on the internet. Why am I showing you this? Because it's the same people that think they can have a high availability thing on a cloud that has multiple regions. And it can't work for this reason. You've got region A. I mean, sometimes it'll work and sometimes it won't work. Sometimes you've got region B, let's say, and then you have stuff in region C. Is there any commonalities between these things? Well, they have to share routes in between them, which means if the routing gets messed up, in any cloud provider, can you be in New Jersey and configure something in Japan? Of course you can. So that means a shared control plane on any of these things. And that means if this control plane's hacked, this network goes down, or the network is hacked, you lose everything too. So what I want you to get here is when to start thinking about, as I start going into these things, what are these devices and where are the real weaknesses? Because I think if you can look at it that way, and I hope that makes sense. If a router doesn't know how to send it somewhere, it drops it. Is that a security enhancement? Yeah. If the switch loses where it's supposed to send traffic to, we've got a problem. So let me show you one more type of thing on switching. And then what I'm going to do is I'm going to start talking about some of the networking types of attacks that occur. And at any point, just bring me back to any of these basic concepts if you desire. What is the network? How does the data get packaged? How are connections set up? So that's really where I just wanted to take it, at least as a beginning level. But let me show you one or two more things that we're talking about with these devices. So if we're going back to this router, let's go back to it just real quick, the first devices we had and what we think of. If we get to this environment, the access point where it's a shared environment, which means everybody can see everybody's traffic, and if two people speak at the same time, everybody gets shut down and has to pause and wait for a period of time. Well, that means this is a very easy network to break into. And it means if you don't have good encryption, everybody can see everybody else's traffic, which is kind of a nightmare. And it means if you just want to be a simple hacker, it's pretty easy to just broadcast straight traffic if you can get onto this network and take the entire network down for anybody that wants to use it. So you're going to need to have some form of making sure you know who gets on that system and keeping track. Now, when we talked about the switch, the key to the switch is it works great. You can segment, who can speak to whom, which is great. You can determine how fast people are allowed to speak to each other, who can speak to each other, who can't speak to each other, who has a route. We can do it all here. But remember how switches forward. Let's assume this is all one big switch right now. And here's the way switches do things. So I want you to understand where things can break. A switch sends unknown data out all ports except the one it came in on. So I've got an unknown frame, don't know where to send it, and it goes in this port. It goes out every other port in that switch. So if I've got 50 ports, I've replicated it out 50 times. If something destroys that table of what goes where, I've got everything going out every port every single time. That's a nightmare. Do you want to see how else this becomes a nightmare? Excuse me. I'm just getting over a bit of the flu. And I say a bit lightly. So when we start looking at things, when we start looking at two switches, let's look at how this, where the challenge could occur and why we have to get really creative with things. So I've got this port out here. I've got a single cable between them. I've got an unknown destination frame. It goes in this port. It goes out all 49 of these and all of these except this port that it came in on. Everybody see so far one frame became 100. Now we're going to do one thing. We're going to now add a second cable. Now look what happens with unknown frames until we do another fix. Got an unknown one single frame, goes out all 49 of these ports, goes out this port, all these ports, and then comes back on this port, and then gets sent out all these 49 ports, and then all they come back into this port. You want to see somebody that can fill a 10 gig Ethernet pipe real quickly? That's what you call a broadcast storm. So when we're dealing with layer 2 or networks, what we've done is there's a protocol called spanning tree that just blocks one link. So you can only use one of the two links. And if this link breaks 50 seconds later, yes, 50 seconds later, this thing says, okay, now you're allowed to speak. So that's typically why we use layer 3 links, but that's called a broadcast storm. So the weaknesses that you have to think about here is this. Unknown traffic goes out all frames. Why does that matter? Well, how about all this? Yo, it's Mike Gibbs coming on port 1. What do you know? Everybody else. It's not, what do you now know? You know I'm on port 1, and you now know how to attack me. What if you don't know where I'm at? Where I'm coming from? Am I more secure? They definitely talk about that in The Art of War. I can tell you that if you've never read it. To let them see you coming effectively. If you think you're coming from the trees, be coming from the forest, or the mountains, or something like that. So I want you to think about that. So do these things make sense? Now on the router. Routers are great. On a router, I can say that this subnet can't speak to this subnet. But yeah, the MAC address is going to be the weakness on the switch. Now, routers and switches are going to look at IP addresses and the headers so they can say this thing talking to this thing at this protocol and port number is good, but this one is not, so we can't go. Got a lot more control at the routers. So we've got lots more things that we can do. But now we've got routing protocols. Routing protocols can be unpredictable at times. Have any of you ever done a CCIE, for example? In case you are a networking person, my CCIE number is 7417. You know what Cisco used to try to do? They'd give you an exam and they made you do certain things by design that would create routing loops everywhere to then see if you could figure out a creative way to solve the routing loop. So the problem was never how to configure that. No one really cared about that. But what they really cared about is, did you know all the other parts of the protocols to figure out how to shut those things off and fix certain things on? So that's where we're going to. So I'm going to talk about some, so the routing protocols are the weakness. If you can hack into a router, can you take down the entire network potentially? Feed bad routing information. Hey, I have the pass to go to New England. And then all over the world sends all their traffic to New England through me, especially if they're not configured very safely. So that's the key to think about there. So now I'm going to go through kind of more that CISSP level and, network security kind of things and plus or minus a few percent either way. But that's really one just to get to first is what is this that we're talking about that's moving? Are there any questions before we move on to the next topic?
Right. So let's see if we have any questions. I'm gonna make ourselves pause here for just a moment. Now remember, this is a cybersecurity fundamentals
Yes.
boot camp. So Mike introduced us to some networking things so that only for the purpose to be able to discuss the security as it relates to the networking. I'm really hoping that Mike does not go down the networking rabbit hole.
No, I would
So
love to, but I
I
know we don't have the
know,
time.
and so I'm afraid that the questions that are going to come in are going to lead us down the networking rabbit hole. So that's why I'm prefacing you, Mike. If the questions come in and lead us down the networking rabbit hole, you steer us towards the security.
Okay.
So Steve, our good friend and stranger Steve, is asking switch hardening or detection triggers might help this.
So we will absolutely be hardening our routers and switches by patching things and also uh, tuning them. So when you get your port, it's typically enabled for things like telnet, plain text port 23 for you to telnet in, and it doesn't have all the security features. So we have to assume every device is not secure. Kubernetes out of the box, completely insecure. Your Mac at home, totally insecure because it's designed for convenience. And in many cases, a lot of the routers and switches have certain services that are actually enabled for convenience, and we definitely have to shut them down and patch them and do things. And of course, we do have IDS, IPS systems, and we'll also talk about logging going to SIEM and source systems and AI even getting involved to help fix these things. So the answer is yes, but the key is we've got to harden everything: cell phones, computers, servers, everything.
Oh, next question. Not sure if it's a question or a statement. Routers create limitations.
I wouldn't say routers create limitations. For the most part, you can't do anything without them. But routers create opportunities for you to enhance security, for you to further segment your system. But like anything else, if the router gets hacked or if the router goes down, you lost something.
All right. Next one is what's the difference between layer two and layer three routing? Okay, network. That's a networking question,
Yeah,
so
that's okay. So
don't take us too far.
so routing is always done at layer three. So what we're really talking about, and this is where I was going to get to next, so I think it's a perfect answer, and then I don't have to cover it next anyway, is this. When we're typically not where I wanted to, let me bear it. We're typically talking, and when I mention layer one, layer two, layer three, is it's a lexicon or terminology that's used by networking professionals through the world. And what we mean by that when we talk about these things are as follows. At the layer one in networking, we're typically speaking about the wire. So I've got a fiber optic cable that sends photons, or I've got a copper wire that sends electrons. So, in tech, we call it bit, but that's the physical layer that we always talk about in networking. And that way, when we say a layer one problem, we know we've got a cable cut or a fiber cut. Now, layer two, and there's a reason I'm getting here, and there's a big security tie-in here, is that's the data link layer. What is that? That's the actual physical card of your firewall, of your hardware. So, if we know that with layer two or Ethernet, it's your MAC address, then we know that we can limit your MAC address and not let you on the network. When we get to layer three, what we're actually talking about is the logical address or the IP address, which we'll talk more about later. Because when you know the IP address of it, you can use things like a firewall or an access list to prevent you. Now, as we start getting up, it's not really part of the networking world. Transport is TCP via UDP. We'll talk about that later and its implications. And then we'll typically talk about what goes on at the presentation layer, which is encryption. But layer two, layer three, we're either talking about the card itself or whether we're talking about the layer three IP, the routing layer, where we could do things like firewalls, access controllers, which we'll talk about.
All right, so we currently have 8 questions to get through.
Okay.
How do modern enterprises mitigate the weaknesses of layer two broadcast domains beyond VLANs? Example 8021X, DHCP snooping, or port security.
Well, they're going to do a whole lot more than that. And that's kind of what we teach in about a 1,000-hour architect program, all of it. But we're talking about things like microsegmenting into VLANs. We're talking about QoS policies to determine who can speak and when they can speak and how much they can speak. We're talking about traffic shaping and policing type strategies to make sure people don't take systems down. We might even be talking about random dropping of traffic and rate limiting of things. So it also might be using some encryption in addition to say an 802.1x. And it's also sending things to packet filters to look and monitor for things. So it's going to be a lot more than that. And it's going to be a lot more related to micro segmenting and multiple layers of things. But it takes a lot of it, and we'll cover more of these as we go through.
All right, next one is, can you please elaborate on Kubernetes not secure?
Yeah, so if you just download and open up Kubernetes, it's not secure out of the box. It's full of security weaknesses, full of networking weaknesses that are designed to make it simple and easy. But you want to lock it down for yourself, then you're going to need to tune it and harden it significantly. Just like when you buy a Windows computer, it's designed to make it real easy for you. And it's got so many things that you don't need on it that the hackers can use to attack you. So if you don't need it, you remove it. Good
So
question, though.
it's kind of like the Louvre Museum's surveillance system's password being the Louvre.
Yes.
Okay. All right. In case you didn't hear about that, that came out of the investigation, I think yesterday or 2 days ago. So that was wonder what Isaac would think of that. All right. Do you recommend microsegmentation at layer two or focus more on layer three boundaries?
If you've got the switches and they're yours and you can turn on both and it's free, I use both. Use as much of the free stuff as you've got.
All right. Do you also face the port 4786 smart install vulnerability that's side, and how do you resolve it?
So Arnold, I'm actually not an engineer, so I've not configured a router or switch in the last 25 years. I'm a network architect and a security architect. But generally speaking, we don't allow any kind of smart install on any router that's going to be used in an enterprise environment, ever.
All right. Given a switch's weakness in an ideal world or architecture, should layer two just be used as dumb forwarders, one to one?
I use layer two for connecting systems. That's it. Meaning plug the systems into the host, and I typically use layer three links because if you're really precision with your routing and you really know what you're doing, you can get faster convergence and you've got load sharing and more control. But the downside of that is you've got to have a couple of very expensive CCIE level network engineers and CCDE level network architects that can design it right. If you can't design it right, well, that changes everything. Then people use more layer two for simplicity.
All right. Does having multiple layers of firewalls help with securing the network?
Very much so. So we're always going to use more than one if it matters, potentially even three. Potentially one firewall from, say, Cisco for general firewall protection, maybe another firewall from Palo Alto because they might detect different things and fix different things. And then we might even put a web application firewall on that web server itself as a three type of firewall situation. Generally speaking, not a cloud provider's one, a more industrial grade one that we would get that have AI behavioral detection probabilities.
Can you expand on the concept of distance vector protocol?
Yes. Very quickly. So we've got two kinds of protocols in networking. One's called the link state, which is you build a map of everything and then you figure out how to get there. And then distance vector is I tell you my routes and you tell your buddy your routes and they tell their buddy their routes. So it's called whisper down the lane routing. And it's about as reliable as whisper down the lane too.
All right, so I'm going to get through a couple more questions and then I'm going to have to make us get back to the content. How does traditional security differ from modern security related to networks such as layer two and three?
So the reality is in a real environment where you own the data center, it didn't change at all. Now, what you have to understand is there are many, many, many weaknesses in cloud computing and security things you can't do. So that forces us to do different things in cloud computing because we don't have the layer two security. We can't do quality of service. We don't have control over the network. And the providers don't either because they have to accommodate everybody else's. So that's when we start using identity as a perimeter and start using more zero trust architectures. But we'll never get to the level of security in the cloud computing environment that we will in the data center. And there are many reasons for that.
All right. If a router is compromised, what is the fastest way to detect it and contain the incident?
So you probably will You probably won't notice it unless somebody decides to inject a bad route and take your systems down. Otherwise, if they can get in your router, they can be monitoring your traffic for years and you might not even know about it. Or they could just stay in there doing other things. And if and when they've got a big plan attack, they can just shut down some interfaces, take your network down in the future, and you won't even know what happened. But the good news is we send our syslog messages to Siemens source servers, and they typically alert you to what's going on.
All right. And Igor is absolutely correct. I am the security control protecting everybody from networking from Mike. How does IPv6 adoption impact enterprise security models, especially in terms of device discovery, addressing neighbor discovery attacks?
Not much. The only difference is we don't have NAT. So if you considered NAT to be security before, you won't have that. If you're like me and you never considered NAT to really be security, it was just a means of hiding an address, then not much changes. Because you're still going to use the same perimeters. Now at this point, if your perimeters are weaker, you have to use more of an identity perimeter, but it doesn't really change much.
All right, and this will be the last one. I'm going to make Mike get back to the content here. When presenting a routing redesign to executive leadership, what's your preferred language for explaining risk reduction and resilience? Do you translate it in terms of RTO, RPO, or operational continuity, or attack surface minimization?
As Cuba Gooding Jr. said in the movie Jerry Maguire, "Show me the money." So I want a company to spend $50 million to refresh their architecture. I'm going to convert their downtime into actual money. So I'm going to look at new revenue opportunities that can go on that bigger network, and I'm going to show them the money. I'm going to build a real calculation. Did it enhance revenue? Did it decrease operating expenses? Did it enable something? But it's all about showing the money. All those other things, they're all meaningless to the person that's going to sign that check. How does it affect their business? That's what matters most.
All right. Um, you ready to get back to the content, Mike?
Yep.
All
Mhm.
right.
Okay, so as we start looking at some of the things that could go on a network, let's kind of take us down the path of we talked about routing protocols. Now, let's talk about what a protocol analyzer is. And if any of you are on a Linux machine or a Mac, and you want to go open a terminal window and type sudo TCP dump, I think it's -I in your Ethernet port, you'll be able to see all those little packets that are going across your screen and what they're actually saying. And that is a protocol analyzer. They discuss it real well in the book, Stevens TCP/IP, one of the best books on networking, which ultimately means security and everything else along the way that's actually out there. So what's really going on here when we actually talk about a protocol analyzer and how is it used? So I can tell you how I used it when I was younger. In fact, they used to call me Sniffer Boy because protocol analyzers used to be called sniffers. And here's realistically what I used to do. I used to stick my protocol analyzer, let's say they had a bunch of switches. I'll tell you why I did it, why I was doing these things. And I was at the world's largest internet service provider. And for some reason, our internet bandwidth was incredibly slow. So this is when I was a senior engineer before I became a network architect. And my manager said, "Mike, figure out why our internet is slow. The world's largest internet service provider, and we're connected directly to a point of presence. What's going on here?" So Mike, the sniffer boy, as they called me at the time, had my little notebook, which was running a sniffer on it. And I'd plug it into the network on a span port, which was a special port that was designed to replicate all the traffic that was going out the VLAN to the sniffer. And I could see every piece of traffic that was going on. Why was our internet traffic so much? Because people were serving music at the time. I think the application was Napster that was installed on people's PCs. People had put backdoors so they could access their computer remotely without using the remote systems thing. An application called PC Anywhere, if I remember correctly. All this stuff, and you'd find it by sticking it on the network. So for network discovery, when we've got a problem, we can stick a protocol analyzer and say, "Hey, this OSPF hello that's going on here, for example, doesn't match this one, and that's our problem. We've got a mismatch." Very easy to figure it out. But the problem is a hacker can get on your network too. And if the hacker gets on your network on a protocol analyzer, they can see any traffic that's on that sniffer that's not encrypted traffic. So what does that mean? Well, in our world, encrypt everything from a security perspective. But that's realistically what we're talking about when we talk about a protocol analyzer. So hacker gets into the system, you can see anything. Now, if we talk about a fiber optic line under the ground, how hard is it going to be for the hacker to get under that, to dig up the highway to find the little fiber optic cable and install a tap, and then bring that tap back to where they're building? It's probably not going to be that easy. But what happens if you can just walk directly in, plug into the network? How many buildings you walked in, plugged in, and you just get on the network? A lot. So there's some common network protocols that I'm going to put on the screen that you probably should remember. And I'll tell you why you should remember them. And then from both an exam perspective, but also for a practicality perspective. Let me show you what I mean over here. And these are protocols. Now, this is how we used to actually access routers and switches, this open telnet, which was plain text. We shouldn't be using it. So this should be blocked. We used to do a lot of FTP work, and some degrees still do, and that's TCP port 20. And why am I saying this? Because if you need to be able to access these systems, which hopefully you don't, you need to allow them through the firewalls and the access lists that are going to be there, which we'll talk about later, which will permit them. SMT, which is mail. Well, most people want to be able to receive mail, whether it's a POP mail account or an IMAP account. These things you'll always have to think about. You may have to let them through the firewall, for example, maybe not. DHCP, which is used for IP address signing, web traffic. Firewalls, if, for example, will have to allow port 443 traffic to a web server. NFS, for any of you that are used to Linux systems connected to file storage, we may have to allow access list open for that. And then SNMP, which is a network management protocol, which we used to use and still do to a degree, that the device, we can look at the devices and then we can see what their health actually is. So we can get access to what's going on in our network. So that concept of that SNMP, that simple network management protocol, was how devices would manage things. And they worked on this concept of an agent and a manager. Looks like my screen, so what do I mean by that? So let's go to let me draw it out for you. So when you understand what's going on, because you will see these monitoring systems in organizations. If we've got all these routers, let's say we're a company and we have 5,000 routers, which is kind of normal, a good 5,000 routers and switches that exists inside of a company. How do you know when the power supply on this router over here is starting not to do well, or this card over here is starting to throw errors? So typically what you have is this concept of SNMP, where you've got the manager. Now the manager is going to be some fancy software package that you can look at that'll show you a map of the network that says this is up and this is down. And then the devices will have some type of an SNMP agent on the device. And this agent will send device to the manager, and the manager can say, okay, well, based upon this, I want you to change your configuration, what have you. So that's that concept of the simple network management protocol you may see or hear in security certifications, and also when you're involved in something to understand what it is. Now, how we send data is going to be very important. And realistically, there's going to be three protocols I want you to understand in networking, because they can be used to send your data from point A to point B. For example, UDP to stream the video to you right now, where I might have all of you. Maybe we'll do an ICMP experiment in a minute. And then there's UDP. So let's talk about the difference. For anything that's real time or not important, we use the user datagram protocol to send data. Now that means I send it and you either get it or you don't. Okay, I'm speaking to you right now, and all of a sudden my internet gets a little icky, and all of a sudden you see some squares on the screen for a couple of minutes. It's because my data didn't reach you. And guess what? We can't resend the data, and here's the reason why. Let's say I had a sentence that said, Cindy is a cat. Well, what happens if the data got retransmitted and we didn't get the word Cindy, for example, and we got is a cat Cindy? It would come out all kinds of crazy and we'd never understand what the message is. So if we lose part of the data, we can't retransmit that data after we've received other data. So for real-time voice and video, we use UDP because it doesn't matter. It's going to be more harmful to get the data a second time than it would be the first time. Now, okay, what if I need you to get the data? What if I need to guarantee that you receive the data? I've got to do it a little different. Do you think it's important sometimes to know that the data is received exactly as it is, and it hasn't been modified or changed? Okay, I have a patient with some hypertension, and I decide to write a prescription for Lorstatin 40 milligrams. What if it doesn't get to the pharmacy at 40 milligrams and it comes in at 400 milligrams, which would be a disaster, or 4 milligrams, which wouldn't be strong enough? That has to be reliable, right? Or how about the direct deposit of your bank account check? You don't want that to get lost along the way. So for other things, we need to use reliable transport. Now, I'm going to show you what we use for that, and I'm going to show you where the weakness in that system is too, because what I want you to understand is there is never a perfect option. If I make you go out there in 400 pounds of body armor to be safe, right? Can you move? And if there's a car speeding at you, can you move out of the way? Probably not. So the point is what we're dealing is everything we do has a trade. We will make something better with what we do, and we will make something worse with every decision we do. So what makes architect, for those of you that desire to become architects, and if you do, join me on the architecture webinar, is really the ability to look at all those trades and say, well, this one, and this one is worth it for our business, but this thing, no way. And being able to know what that is. So for later in your career, or if that's what you want to do, I want you to understand that. Now, let's talk about how TCP sets up a connection. And I want you to understand some things that we'll talk about along the way. So how would this work? Now, if I went out there and I wanted to know someone got my message, I'd ask them to repeat it back to me. Chris, can you meet me at 6 p.m. on Zoom? He'll say, Mike, I want to make sure I got this right. Did you want to meet on Zoom at 6 p.m.? And I'm going to say yes. And we're not going to have a mistake that way. So how does TCP work? Well, let's say we've got two individuals. On this side, we've got Cindy the cat, and Cindy the cat decides that she wants to go buy some ahi grade tuna. So there's this place that's her favorite place. It's called Cindy's Favorite Ahi Tuna and Shrimp. And I hope I didn't steal a real name. I doubt it.com. So let's say Cindy wants to reach here. So the first thing Cindy does is to this web server, we'll get the routers and switches along the way, is Cindy says, can I speak to you? Because I really want to look at your tuna and shrimp because I'm hungry. And that message itself is called the TCP SYN. I didn't make it up. And the SYN means for synchronize or open up a connection. Now, of course, when the website Cindy's Favorite Tuna and Shrimp.com sees Cindy wants to use her daddy's credit card and buy shrimp, of course they say, Cindy, I acknowledge your connection. And not only do I acknowledge a connection, but like to open a full conversation with you. So what happens is Cindy sends an acknowledgement that to mine, and then she has to send and open the connection with Cindy from the website. And then, of course, Cindy says, of course, I'd like to talk to you because I want to use my daddy's credit card and buy some ahi tuna, which she does all the time. And then Cindy will say, well, okay, I acknowledge your request to open up a connection. And that's the TCP three-way handshake. So I'm going to show you two things. So the first thing that I want you to understand is, let's say we've got this server. Let's say this server can take 5,000 open connections at any one time. Open connections. So now that you know how it's supposed to work, what happens if Cindy the cat is not Cindy the cat? So everybody's heard of the evil cat that bites you. So I'm going to call this the evil cat that bites you. And I think all cats are great, but that's neither here nor there. But we'll call this the evil cat that bites you. Now, the evil cat that bites you decides it doesn't want Cindy to get her shrimp. So what the evil cat that bites you does is she sends about 5,000 TCP open a connection. And then when the website responds back to her and says, hey, I'd like to open a connection, she never does. So this evil, the cat that bites you, opens up all these connections, and now the server is DDoSed and it can no longer handle the connections. So that is one thing that we're going to have to look out now that you understand the way the TCP handshake works. Now, the other thing that you need to understand via TCP when we describe this is as follows. So let's say we've got two people that are trying to talk to each other, Cindy and Sunny. They want to share stories about where they can get better salmon and seafood. And the two of them are speaking to each other. Now, these two are having a perfectly fine kind of conversation, and there's no problem. Forget where I was headed with the third attack over here. But forget where I was headed with that. But that's what I want you to see. If we get too many half-open connections, we have a problem. Actually, here's what I wanted to say. So let's also see the way TCP sends traffic is this. Cindy sends one message to Sunny, and Sunny says, Mike, there's Cindy, got your message. So then Cindy says, oh, the network's clear. So Cindy sends two messages to Sunny, and then Sunny says, got your two messages. You can send more. So then Cindy sends four messages at a time, and Sunny says, I'm getting it all. Keep sending it. So Cindy sends 8 messages at a time. Sunny says, keep sending it. Now, Cindy sends 16 messages. Sunny drops it. Now Cindy starts sending out at 1, and that process occurs. Now let's imagine out of no reason that somehow somebody found out there was free shrimp, tuna, and everything else. And now we've got we've got a lot more cats. We've got the cat. I don't know what to call it. I'll call it Felix. Now we not only do we have Felix, we've got Whiskers. Now they all start sending back and forth a lot of data to Cindy at the time, and we have a 1 gig link. And somehow Cindy, Sunny, and Whiskers and Felix, they all send so much they filled up the 1 gig link and all the traffic dropped. Everything has to stop and start being resent. So even if this is 10 gigs, if we have a lot of start stops along the way, ultimately what we can happen is this throughput can become less to nothing. So what do we network architects do? Well, we may apply certain types of policies to these types of links, or our engineers will do it, but it'll be part of our design where it says, if this thing's reaching 80% and it's all TCP, maybe drop 20% of their traffic so we don't get all these people to retransmit at the same time and take down the link. So that's kind of where I wanted to show you with that protocol itself. It's a very reliable protocol, but the weakness is in it. If I send a whole bunch of half opens to you, you're going to be very vulnerable. So what's the cure to that? Block the half opens before they get to you. And typically a content delivery network, which we'll talk about later, will do more of those things. Make it that you don't get the bad things in the first place. So that's the next thing that I wanted to kind of walk through. So it's that 3-way handshake. It's that flow control. So the next thing that I want you to think about networking wise is going to be as follows. Do you all realize that you can connect to any website you want by just entering the IP address in your browser? Now, my wife sees a little bit of a difference. She's got 160 IQ. She can remember the things that I said that were stupid back in 1993 at the date, the time, and the exact words. Now, that is not me. So when I ask her what phone number did I have as a child, she can still tell you. Now, for the rest of us, how many people could remember how to get to Cisco's website or IBM's website or Dell's website or Apple's website? Or for me, I go to the PetSmart website because my cat likes these things called Bonkers Purr Pops that she goes crazy for. But anyway, so there are a few websites that I go to. I can't remember. So that's the concept of the domain name system. And all that really was a directory of ways to say, here's a user-friendly name that you can remember instead of that weird name. Now, that could enhance our availability in some ways, and here's the reason why. If I say go to Leo's IP address and Leo's IP address is down, can you reach Leo? No. But if I can say go to Leo and you knew to go to Leo, and if Leo wasn't there, you got routed to the second Leo's computer or his second internet address, you can still see Leo. So when we're talking about DNS, it's going to be everywhere. Everywhere. Now, where's the real challenge with DNS? It's networking, and most people don't understand networking. So why do you hear of DNS outages all the time and network outages all the time? Because people don't understand networking. They make a change. They don't understand what the change is, and the whole system comes crashing down. So I'm going to at least give you an intro level of what is DNS. DNS is a means to map a name to an IP address. So when you type www.gocloudcareers.com, you will come to our IP address. And you know what? For all of you that want to have fun, pick a website, actually open a terminal window or a Windows PowerShell window and type NS in NS, which means name server, but make it NS. And in one word, type lookup. So NS, November Sierra, Lima, Oscar, Oscar, Kilo, Uniform Papa, and then leave a space and then type www.anywebsiteyouwant.com. And you'll be able to see the IP address that it has, or at least the IP address of their content delivery network. And why is that? Because I promise you can't remember the address yourself. And no one could for thousands of different websites. So that's the concept of the DNS system of what we're using. Now, we look at it, I want you to think of there's really three components of any DNS name. Very simple. There's the host name, what you name the computer. There is the domain name, and then there's a top level domain. So let's play with it. We'll look at it so you kind of get the concept of where it would come from. So let's say we're going to look at this. And first I'll make it pure host name, and then I'll make it pure something that's going to look more like something you're used to saying. So here we go. Let's make this a pure host name, a fully qualified domain. So this could be cindy.gocloudcareers.net. That is what's called a fully qualified domain name because what are we actually .com? I'm sorry, when I was thinking .net. So why is it a fully qualified domain name? It includes three different things. It includes the Cindy, which is the host name that we're actually talking about. And it's clear I like my cat way too much. So Cindy would be the host name. Now GoCloud Careers would be the registered domain. And then the top level domain would be .com, .net, .org, .gr for my family in Greece, for example, .edu for a university. So that goes what's into it. Now, typically you'll see it look like something like this. Now that is a fully qualified domain name that will point you to the two IP addresses of our web server. Because, when it comes to availability, one is none, two is one, and three is better. Three is greater than two. So you always have to use more than one. So that's what we're getting into in a fully qualified domain. Now, by itself, and I'm not a DNS person by any stretch of the imagination, that's typically much more sysadmin work than, say, network architect work or security architect work. But understand the system itself had some weaknesses in it, specifically related to making sure you are who you claim to be. So what are one of these great ways that we can make sure that everybody is who they claim to be? We can use encryption. We can use that an encryption, for example, asymmetric encryption, which is a certificate that proves you are who you claim to be. And oh, by the way, please see it today. I made a video on phishing resistant multi-factor authentication. And not only did I release that, I talked about public key cryptography and got 2% geeky because it's kind of fun. So please do check that out. I'll make sure my team drops that down because it'll definitely help you understand this more. But DNS now has something called DNSSec, which is basically what they did is they added some security features to prevent things like DNS spoofing, where things would pretend to be who they're not claiming to be, or where your cache would be poisoned and you'd be going to a wrong place, for example. So that's based on cryptography. And work on the assumption that you need to use DNSSec on anything that matters, because it'll help mitigate some of the types of attacks that you could have. So what is DNS poisoning? Well, if we know that www.cisco.com gets you to Cisco, and I know you go to Cisco all the time, what if I poison your cache so I think you're going to Cisco and you're going to a lookalike page that looks like Cisco, and then you log in and I grab your credentials? That's not good, right? So if I make your DNS system think I'm pointing you to the same page, but I take you somewhere else, this is a problem. No, this is no different than telling a child, I'd like to buy you ice cream, and then they get kidnapped. But it's really the same kind of thing. They're tricking you into going somewhere, and they're hoping that you're weak. So that's really what we're talking about with some kinds of DNS poisoning. Now, there's another concept called DNS farming, where they redirect you your routed URLs to another server. And sometimes they can do it by changing access to the DNS settings to point to an invalid server. Or, does anybody know that little file inside your computer? It's called /etc hosts that enables you to like put some information that says type cat and it'll go to Cindy, type dog and it'll be to the golden retriever that I always wanted, even though I have allergies. Type D and it gets you, I don't know, a Maine Coon, for example, whatever you have. So like, those types of things. So DNS farming is when people start creating servers and point you to the wrong place. Now, obviously, if you're using a certificate and know that the certificate doesn't match, you'll know it's the wrong place. But if you're not, you won't get that. So if we've got DNS systems, we obviously want to patch them. We typically want to monitor and log what's going on. And we always have to make sure our users know what's going on. Now, there's another type of concept called domain hijacking. And if the domain is registered for Cindy to the cat, and Cindy walks around every night and says Cindy doesn't like this cat and Cindy and this other cat are enemies, if that other cat is really smart and it can go hack into Cindy's DNS account, that other cat can point Cindy's legitimate website into something that would be totally illegitimate by by hacking into the DNS server. Now, this one I'm going to talk about next is something I really want you to look at real carefully, because this is something that may protect you from real things. How many of you have seen the difference between the Greek letter alpha and the American letter A or the English letter A? Pretty similar. Pretty similar. How many Cyrillic letters look a little bit like English letters? How many Greek letters look a little bit like English letters? So what you'll see people do is they'll make a website that's going to look just like yours, but they're going to replace a character with a near lookalike character from another language. So it will therefore be a different DNS address. So that's called typo squatting.
I saw one, I actually saw one today, Mike, that was trying to spoof Microsoft, and it was the
Yeah.
letter R and the letter N right next to each other. And so if you're not it, on certain display fonts on like phones and stuff, the R and N right next to each other look just like an M.
Yeah.
And so it says rmicrosoft.com, but if you're
Yeah.
not glancing, it looks exactly like Microsoft.
And that's, yeah. And they start talking about that's what they're calling a homograph attack now because it looks the same. You can't tell, but it is. Great example, Chris. And the point is, we're all seeing them now, all of them. And these are just the kind of things that are going on. So there's one other type of thing that I want you to think about in internet protocol in the way we send data. So if UDP is sent for voice and video, like your Netflix video, or for me, I just saw this great video of Heart with like this London Philharmonic Orchestra. It was really cool. And, I watched that. I was like, wow, this is really great. So, that came via UDP. Now, I have reliable things that I need to send to you. I send via TCP. But what if I want to check and see if something's alive on the internet? And what do I mean by that? So I want to go to my website, and for some reason I can't reach it. I'm probably going to go see if I can reach the Cisco website because the people at Cisco know how to make a really high available website. And if the Cisco website and mine is not there, I figure the issues on my own. Now, there's much more sophisticated ways to troubleshoot, but I'm not an engineer. Now, if that Cisco site's up and I'm not, I start looking, okay, what's going on? Then I start doing trace routes to different places on the internet. And then I say, okay, there's got to be something with my DNS, my load balancer, or my firewall rule, and we figure out what it is and it's done. But that's the key. We have a means to test this. So why don't we all, just for fun, open up a terminal window or a Windows PowerShell window? We're going to send an ICMP message. Now, for the most part, this concept of the Internet Control Protocol, messaging protocol is free to diagnose networks. So pick any website you want so we don't accidentally DDoS anybody because I don't know how many people here, and type from that terminal window ping, leave a space, PING, so Papa, Indian, November, Golf, if you want to use the phonetic alphabet, then whatever website you desire, www.any.com. And what you're going to see, hopefully, is a couple of messages going back, an ICMP, and then an ICMP message reply, which is going to tell you a few things. Your packet number, how long it took you to reach point A to point B, and you're also going to see the latency of it. And if the latency looks good, like it's 5 milliseconds, 5 milliseconds, 5 milliseconds, 5 milliseconds, 5 milliseconds, you've got a great connection to it. Now, what if it's 5 milliseconds, 20 milliseconds, 3 milliseconds, 80 milliseconds? Now, that is not a line that's got very reliable speeds. That's called jitter or variations in latency. That's not going to do well with video. Which means if I wanted to take your video network down, I could just send a whole lot of traffic. And unless you put some kind of a service on your network, like quality of service, it's pretty easy to take a system down. So that's what ICMP is used for. Now, it is a very good way for us to determine if something exists. And if I can't find between where my data is getting lost to on the way to Chris's house, what I'll do is on a Unix machine, I'll type traceroute. I think on Windows it's trace RT. And I will type www.sendythecat or whatever website I want to go.com. And that's realistically speaking what would be using to do that. Now, if I can send messages that make people reply, could I potentially use those messages for harm? First, can I do a ping and determine like how much data I can send on the path, like, the MT or the packets? Yes, I can. Can I discover what devices exist and what devices don't exist? Yes, I can. And if a hacker sends what's called a ping of death, which is a certain type of ping, that could also take down a web server. So the tools that we use for diagnosis and discovery, guess what? Our hackers use to hurt us. So we need to determine which interfaces should be allowed to receive ICMP. If I don't need to know your IP address or whether you're there or not until other than just being able to pick up your website, I can block it. And many companies block ICMP for that reason. Okay, so ARP. When we went back to the switch, and I'll go back to that diagram fairly quickly that we drew live on that switch. I'll go back and draw. We drew a lot of drawings today. Okay, so let's actually, and I'll make this as a new drawing. So let's say I have a data center. And in this data center, I have 5,000 servers. Actually, they're bigger servers now. So let's just say 500 servers and 3,000 users that are plugged into the switches inside of this campus. And that's going to 5,000 remote locations. I'm going to have some pretty big network. So let's say I've got a bunch of VLANs, and the VLANs are all across a bunch of switches, and they're what's called trunked together. So, and before I showed you the layer 2 version of this, but this in this case is going to be, say, the layer 3 version. For argument's sake, to make this stuff really easy, the two users are going to be in the same subnet. So this user is going to be 2.168.2.253. Actually, just copy. Make sure these are both /24 so you can see they're in the same subnet. So I've got two sets of users that are sitting in the same subnet. And the way this worked the first time is when the user with this IP address at layer 3 says, I want to speak to 192.168.2.253, what has to happen is the IP stack on his computer or her computer has to say, I want to talk to this MAC address. So it does something called an ARP, which is this ARP resolution protocol, which is how we map names to IP address. So this user sends this broadcast message. It'll look on a sniffer. It'll say ARP, who has, and then it will be the MAC address of this IP address. And then this device will respond, I have the MAC address. And then ultimately, as we talked about earlier, the switches will build a table from that ARP process to get data from point A to point B. If someone were to spoof this MAC address, for example, let's say this MAC address, let me draw one, make sure I get it right. So 12:3:4:56:1 alpha 2 foxtrot. I need 6 of these. How many did I create? Octets. 1, 2, 3, 4, 5. I need one more. Okay, so if that's this MAC address for real, let's pick a different MAC address for the other one so you can see how they're unique. Because every device by default has to have its own. So let's make this one 13 and change that Charlie Foxtrot to Charlie Bravo. We should be good to go. This looks a different enough MAC address. Very different. So now this device knows to reach this device going out this and goes out of that switch port. And then some hacker decides to plant a bunch of bad fake MAC addresses on this port. Specifically, it pops this MAC address off of this port and it convinces the switch that it has it. Does the data go here? Or does the data go here? Well, it'll go to whatever the switch remembers as the first, which in many cases where the hacker puts it. So that's an ARP attack. So the only way to protect against this is to not let anybody plug into the network that shouldn't. So we will talk about things like 802.1x, but how many offices just have an Ethernet port that's just sitting there? I've been to buildings that have multiple layers of armed guards, and you could just plug right into the network, and they didn't have network authentication of any kind. Plug in and you're done. So we're going to talk later about physical security to prevent against these, because you can't prevent it all just by touching the devices. So if I know that we're in an environment where other people can see our traffic, is that concerning? It can be desperately concerning. Dr. Banjava, this is Mike Gibbs. I'm calling about a patient. Patient is in the ICU. Their blood pressure has decreased to 80 systolic. I've asked the nurses to start a dobutamine drip as well as a neosynephrine drip and titrate to a systolic BP of 110. Now, if I had the patient message in there and it was a patient, that could be bad information. If the hacker could have changed the titrate to dopamine drip, and we don't typically use dobutamine like we used to, but that could also be a problem. So the point is we have to be very careful of making sure that what messages get heard by whom. So where does it matter traditionally? If you're in my house, and I want you to understand old security versus new security, if you're in my house, do I assume you're a security threat? Probably not, which means that I might use discretion in what I say. For example, if my wife and I were talking about getting a ragdoll cat or a Maine Coon because I want one, and I know my cat Cindy doesn't like cats, I might have that discussion in her when my cat's not there so she wouldn't understand and get angry at me. So I might determine what the limit, but all in all, when we think about this, it puts us into that combination where we always have to constantly think about this. Who's there and who can hear? Now, on the internet, it's pretty terrifying, right? Everybody's there. So what do? We encrypt our traffic. Now, I don't know about you, but no matter where you're at in the world, people find a way to stay private. Lots of private languages out there that people were meant not to hear or not to understand for good reasons. So what do? Something very similar. If we are on a shared medium, we must use some flavor of encryption, some flavor of it. Now, if you speak to somebody in another language in the room and you're only two people that speak that language, it's some form of weak encryption. So what we're going to do next, and I think maybe that's a good break, is we're going to talk about the two types of network and encryption that we typically use, where we use them, and the strengths and weaknesses of each option. And before we do that, can you tell me another shared medium where your stuff is on the same network as other people's stuff, where your server is on the same server as somebody else, where your storage is on the same environment as somebody else, and if somebody walks in and takes that hardware out, your stuff goes with it? And this can happen anytime where the FBI decides to warn a certain set of computers. That's called computing. So that's why we need, because we have all those big weaknesses, to do things more like zero trust. So let's take some questions, and then we'll have some fun with encryption.
Right. So one of our questions from earlier, what's your take on AWS Sovereign Cloud? Do you see it as an improvement in terms of security architecture and operational autonomy, or do you see it more as a regulatory response to satisfy political and compliance requirements?
So realistically speaking, if I had data that needed to be so secure where I needed 100% control over it, I'd manage it myself because it's the only real secure way to do it. Now, what if I wanted somebody to manage it for me because I realize I'm probably not the best at managing it myself? And I know the risks of cloud computing are real because it's a shared system. And I know that if my stuff is on the same systems as everybody else's stuff, every state actor in the entire world is going to hack into that system. And not only will they get access to all the United States businesses, but the US government stuff. And believe me, if that was the case, everybody would put the money and easily be able to do it. Would I do that? And the answer is no, it'd be crazy. So what they did is they have a separate cloud for things that need to be more secure. So that way, if the public cloud gets hacked, they're not actually getting inside of these government systems and more secure systems. So personally, I think it would probably be better to do it themselves and build a much more secure environment. But if you're going to use someone, it needs to be a sovereign cloud, not on the same cloud as everybody else. Because you have to remember, nothing gets more secure with cloud computing. And you always have to look at this. If you just look at the two different risks, if I mess up in the data center, you can hack me, right? If I mess up my own systems in the cloud, you can still hack me. But if the cloud provider messes up, you can still hack me through their mistake. So it's a new attack vector that we always have to be careful about. Good question.
All right. Let us know if you've got any questions. I will go with another one that came in earlier while we wait for that. So earlier we were asked, should layer 2 be the first priority to secure in order to protect against network-based attacks and unauthorized traffic manipulation?
I would use everything that I have that I can. So if that means if I have my own switches, if I have in my own data center, if I can create a private VLAN where two servers in the same VLAN can't even speak to each other, I'm going to do it. And then I'm going to have other VLANs to make sure that other servers can't talk to each other. And then if I can do access lists at layer 2 and filtering and QoS at layer 2, I will. And then at layer 3, I'll still do things, ACLs, packet filters. I'm going to use all of it. Because at the end of the day, any one thing can be defeated. You broke through my Cisco firewall. That doesn't mean you necessarily got through my Palo Alto firewall. If you got through my Palo Alto firewall, it doesn't mean you can necessarily breach my Fortinet firewall. And when you finally got past my Fortinet firewall, heck, I'm going to have another firewall on the web server that's going to keep you entertained for a while. And then after that, I'm going to be so micro-segmented that it's going to take near forever for you to get something. So I'm going to use it all to the point until the point it's going to be affecting the way the company works and the employee workflow, and it's going to cause more harm than good. But some things that we get are free, and some of those free things can make a huge difference.
Right. And can you identify a rogue system connected to your network?
Yes, if you're monitoring your networks well enough, and you're really looking, and you've got intrusion detection systems that are looking for weird anomalies going on, and all your syslogs and all your files are going to really good Siemens source systems, and they're using AI, and you've got really, really good IAM systems where every time somebody tries to access something, every request is going to be requested and it's going to go through the system and you're going to get a log. You will catch it earlier. Now, it might take companies 3 months, 6 months, or more to even know they've been hacked. Big companies, too, especially if the hackers are good at what they do. But generally speaking, that's why you need so many monitoring systems. And that's why I might use, at least in the perimeter, a next generation firewall, a second series of next generation firewalls, and IDS IPS systems, and even including some data loss prevention stuff that's going to monitor the egress as well, because I have to assume everything that can go wrong will go wrong. Every weaknesses will be exploited. And once you get past one, I want you to have another. So whether it's like an onion or my grandmother used to have these Russian dolls. They were really impressive. We had one, it was like a big doll and you opened it up and then there was another doll and then there was another one and another one and they got real small in the center. That's the way I like to build my security, where each time you remove a lever, I got to deal with this now, to give us time to find it and stop it whenever possible.
All right. So the next question, and multi-cloud routing, identity and location are decoupled. How do you define inside or outside in an architecture where packets, users, and policies all exist in superposition?
Well, first, what makes you think the identity is decoupled? The identity is going to be very coupled. We won't be using those cloud provider systems. We're going to be federated into a single system. So we will have our identities very coupled. We won't use the cloud providers like I made my own thing. We're going to use the industrial tools in all clouds to monitor everything at all times. So what was the other question, part of that question? Because
It's how do you define inside or outside in an architecture where packets, users, and policies all exist in superposition?
very simple. Internal things are internal and have a private address, and you can only be on the private network to reach them. Just like we've used for the last couple of decades with private lines, for example. External will be things that are associated to the internet that you can attach from the internet. You don't need any kind of connection to reach on the internet. And it's a great question that you asked that.
Next one, what do you do when an attacker logs in to your router and leaves a footprint?
Find out how they got into your router and restore the configuration to what you know to be good.
All right. And in the future, digital assistants and AI programs will connect directly to each other to share data. Uh, how do we make sure they only talk to trusted systems and not fake or hacked ones?
We have to determine who they're willing to attach to, and that's using certificates and using trusted versions, for example. I just won't let you connect to anybody other than these three sources.
And I think
And I
we,
can block.
Jose, I think I would like to, I think I could be completely wrong, but I think we kind of touched on that as it relates to identity and access management of
Yeah.
non-people roles in last week's class lesson with Isaac. Um, I think that kind of would go towards
Mhm.
this topic
Yeah.
of bots and
Yeah.
entities that are going to communicate with each other independent of human interaction. I feel like we talked about that with Isaac last week. So go back and take a look at that recording when you've got the time. Of course, it's another 4 hour session,
Yeah.
but I think that'll give you a
Yeah. Cool.
good idea there. So those are all the questions so far.
Okay.
We can move on, and then, of course, we'll get back to questions again in a little bit.
Wonderful. So let's talk a little bit about network encryption. If we're all in the same room, it's a problem, right? But what if I could find a way to make sure that I knew that you were who you were supposed to be, and I could send the message and make sure the message hasn't been changed, and after the fact, make sure you couldn't say you didn't have the conversation with me. That'd be kind of cool, wouldn't it? So the answer is we can do this. So at the end of the day, here's what we're trying to avoid. Okay, so we're trying to avoid a couple of things. So the first thing we're going to want to avoid is something called the man-in-the-middle attack. And what is that? Common spy thing, honestly, but the hackers use it as well. So let's say I've never met you before, and I want to meet Tyron for the first time. I've never met him. I've never seen him. I get on a plane. I fly to Cape Town. I've never seen Tyron before. And all of a sudden, somebody says, holding a stand that says, "Hi, Mike Gibbs, it's Tyron." And I get in his car and it's not Tyron. And then I give him the secret formula to the new drug that I was developing in this pharmaceutical company. And then that company releases the new drug before we do, and we go out of business after spending $2 billion on R&D. It's called the man-in-the-middle attack. Now, me personally, I'd get a photo with Tyron before I'd actually get on that plane. I'd make sure that he is who he claims to be. I know who he looks like, know where he lives, and probably meet him in his house. I know it's Tyron that way because he's got a couple of things, something he has, something he knows. So he'd have the same house that's his registered address, and I'd ask him a question and he'd know it. And that, but there's that. So we need to make sure we know who we're communicating with, but also should other people be able to hear it? And should other people be able to know that I'm communicating with Tyron, or does it matter or not? So I want you to think about that from a hacker perspective. Tyron is the CEO of a pharmaceutical company. I am the CEO of a pharmaceutical company. Tyron and I are fierce competitors. We're both in the same circles, but we hate each other because each one of us keeps crushing each other. And everybody knows it. All of a sudden, Tyron and I start sending internet traffic to each other for 4 hours a day for 6 months straight. Any hypotheses what's going on? And how you would use that information? Tell you what, I would signal to me. Two CEOs that don't love each other in competitive businesses that are talking every day. Something's going on here and it's pretty big. Steve's halfway there. There's a merger going on. Now, if you have that information, do you have actions? I'll tell you. You can now make probably some pretty good investments on which stock's going up and which stock's going down as part of the merger. I'm sure you can make some money on that. Now, what if you wanted to block the merger? Could you do things to potentially do that along the way? Potentially, yes, as well, and cause trouble, get regulators involved, get legislators involved to block it. So whenever we think about encryption, we have to think about what we're talking about. Does it matter? I talk to Tyron as often as I can. I don't have a lot of time, but he's great, and I talk to him when I can. Is my concern that somebody knows that Tyron and I speak? No. Why do we care? But other times it might matter. So when we think about encryption, we're going to talk, realistically speaking, about two kinds. We're going to discuss IPSEC, and we're going to discuss this concept of SSL TLS type security. And they are different in what they can do. And they are different in the way they work. So I'm going to first start with TLS security, which is what most of you are familiar with. Go to any website, see that cute little lock on the thing where it says HTTPS? That's TLS security. And what's going on is you're using a certificate on that website, and that's proving that that website is who it claims to be, so you can trust it. And what it's going to do is it's going to encrypt your traffic going between you and them. And what will it encrypt? It will encrypt the payload of the traffic. The payload of the traffic. It will not encrypt all of the traffic. So you will still see the headers, but not the payload. So you will have Mike Gibbs's IP address talking to Tyron's IP address. If it doesn't matter, this is perfect. But if it does matter, does this sound like an effective form of security? No. So we have to understand that. Now, I want you to think about how critical this is. Tyron became a nurse. Tyron's a nurse working in the intensive care unit, no, the cardiac care unit. And a patient, for example, is running a very rapid heartbeat called SVT. And I decide that maybe I'll give that patient amiodarone. If I order an amiodarone drip and tell Tyron that, Tyron must bet that amiodarone drip right. It's the right dosage. Because if not, somebody's going to die. So I need to know that data has not been changed. So when we use any form of encryption, not only do I know that Tyron is who he claims to be because of the exchange of the keys and the way it's going to occur, but I'm going to hash the message. So if I say prescribe a patient with a chest pain 4 milligrams of IV morphine, it's not going to be changed to 40 milligrams along the way. It's going to stay at 4 milligrams of IV morphine for that patient with active chest pain going through an active heart attack. So there's going to be a hash, and I'm going to show you what that looks like. And there's typically going to be a sequence number of it. So what does that mean? So here's what it's going to look like. We'll map it out. We'll have some fun with it. If this is the packet if this is the data that's going through me and to me and Tyron from Mike, and I want to communicate with Tyron, here's what happens. So this is the data that I want to send. Now, realistically speaking, I'm going to have a header on the packet. There's going to be a few other things in this piece of data, but I want to basically keep it kind of simple. There's typically a footer or something at the edge of the packet and a few other things that are here. But the header of the packet is going to tell us a lot of things that we need to know. It's going to tell us, and I'm going to show you why I'm getting here. It's going to tell us the source address. It's going to, for the most part, tell us the protocol, like whether it's TCP or UDP, and the headers that we're going to have. In fact, I'm trying to simplify this a little bit. We'll get the protocol. We'll get the port numbers, like going to TCP port 443, for example. We're going to get something called the type of service bit, which can really help us as well. And we're going to get a few other things like a frame check sequence and things that may change. But what I want you to really get is the source and destination address. This is what's going to be in the header of this packet. And you're still going to be able to see that with this TLS. So you're going to see this and then the data. And what's going to happen to do is we're going to encrypt the data. And without the decryption key, what you're going to see is something when I was a kid, we used to call gibberish. So this is going to be encrypted. Now, do you think anything in our networking world is going to use this source address, destination address, protocol number, and port number? Why on earth would Mike talk about what's in the header of an IP packet when he's talking about fundamentals? I'm going to tell you this is the reason almost everybody's failed every security interview I've ever given them. Any ideas? Well, does a firewall look at the source and destination address, a protocol, and a port number for security? Yes. Does an access list that we would use on a provider, on a router or a switch or a cloud provider use the protocol and port number? When the router sends an error message, does it send it to the Siemens source systems with an IP address, protocol, and port number, source and destination address so we can track it? When the AI in our firewalls and intrusion detection prevention systems is looking and saying, this one IP address is doing something funny, let's block it, it's going to be using that. So everything that we need when Cindy the cat tries to log in from Nepetomos, Greece, when I know she's supposed to be in Port St. Lucie, Florida, because she's not good at an airplane and she's not at the family house in Nepetomos, Greece. When Cindy tries to log in from Nepetomos, Greece, and I look at that IP address header of hers, I want to block it because I know she's sitting right next to me in Port St. Lucie, Florida. So almost everything we have in security is going to look at that protocol or port number. Now, it's kind of sad. I like to travel, or for work, I used to be in like 5 different countries a week. Now, when that happens, each country you go to, they stamp your passport protocol and port number. How many times do you think I got in the random search line? Oh, I see you're here and here. We need a specialist random search. All right, fine, whatever. Oh, you went to this country. We need to random search you. What is it doing? It's looking at the places that I've been and running some kind of security algorithm. Well, I go to a lot of places. I do work all over the world. I got to meet great people all over. That's all I got to learn. But, you know, that's the point is we're constantly looking at these systems. So that's why I really wanted to get the concept of it. We're getting in that header. So now, now you see what we're dealing with that. I want you to see the other kind of encryption. That's going to be IPSEC. So we'll have some fun with that too. We'll draw it all out. So in IPSEC, typically speaking, here's what we have. And it can be done via a lot of ways. But let's say this is a router. And let's say this is another router. And this could actually be a wire between these two routers. It doesn't have to be an internet connection for encryption. Now, here's what we do with the, oops, what did I just do there? Here's the way IPSEC encryption works. What we do is that we take the packet itself. So here's the packet itself. So here the packet's the header. Then we have the payload of the packet. And then we put a different header on it, and it's going to look like a tunnel. And it's going to put an IPSEC header in it. And what happens is this IPSEC basically puts the packet into a tunnel, and nothing gets seen along the way because it's going to go. Let's put it into here. So we've got our data as it stands. It then goes into the tunnel. Look at this way. We encrypt the header, we encrypt the packet. It goes inside of the tunnel. So inside of the tunnel, nobody can see that I'm speaking to Tyron, for example, and nobody can see anything. And when it gets out the tunnel, it's decrypted, the header is removed, and the packet goes where it's supposed to be. So that's typically an IPsec tunnel. Now, where do we use this? Everywhere. So when you work from home, and you pick up your VPN client and you create an IPsec connection, that's typically an IPsec VPN. Not always, but typically if there's a client, it's a VPN. So you're often using that in work. And you may also be using it, for example, let's say you were working with an environment where you didn't need perfect network connectivity. Actually, you know what? Let me just show you the difference real quick. Let me show you well, there's a couple wide area network options, but let me show you the two basic options that you can use. Option one is this, and this is what you buy when you need guaranteed speed performance, and it's the most secure. And here's this. Let's say this is your New York office. You want to connect to your London office. You call your phone company, like an AT&T or Verizon, and you say, I would like a 1 gig private line. And they create this 1 gig private line between you and the New York office. It's basically a wire that's created for you. So it looks like a wire, feels like a wire, and it is completely separated from everybody else's traffic. So this is yours. You own it. So the only way a hacker could get access to this is if they could actually dig under the ground and actually get access to the phone company system. So generally speaking, this is relatively secure. But what you could still do is you can then and this is what we do with sensitive data, is we take our data and then we put it in an IPsec tunnel over the private line, and then it's encrypted along the way. So that's option one, and that's typically speaking the highest security, highest performance. Option two is this. We connect, say, the New York office to the internet. We connect the London office to the internet. And then we create a virtual tunnel through the internet. And that's typically where we would use an IPsec VPN to connect these two sites. But they're not equal. Here I bought a wire from Verizon and they said, I guarantee you 1 gigabit per second and it will never be more than 4 milliseconds latency because you own the wire. Here I am assuming that I am using the internet, and if the internet gets my traffic point A to point B, fine. If it doesn't get it, there's no guarantees on the internet. So critical when it doesn't matter so much. But that's typically how we would connect things. Now, how critical are these networks? Let's say you have a bank and all the storage is attached to the network. All the servers are attached to the network. All the traders' computers are attached to the network. And the phones are now attached to the network. What happens when the network goes down? Can you pick up your IP phone and make a phone call? Can you start a Zoom session with someone? You just bought 10,000 of shares for a client this thing and the price is tanking and you want to sell it and you can't. The client going to be happy that they lost $1 million because your computer system was down that day? So when we start talking about converged networking where everything's on the network, how critical does that network become? So if you wonder why I'm spending too much time on network security, potentially speaking, out of the 5 days, is because 50% of the security we can do effectively is on the network. And this is the one thing that it goes down, everything goes down. Especially in a cloud computing environment where everything is hyper-converged. So how do we get a little more secure in any environment? So you ever have two cats that don't like each other, or seen two cats that are neighbors and each cat doesn't like each other for the reason why you can't figure it out? My cat hates the cat that comes to visit her every day. The cat comes on the door, scratches on the door, waits for Cindy to come out, and then Cindy hisses at it. It's a beautiful cat that comes to play with her, but she doesn't want to play. What happens if I open the door and I let Cindy play with that cat? I can tell you right now. Cindy's 7 pounds. Cindy goes and attacks this 24-pound cat. And then the 24-pound cat attacks Cindy back. And then Cindy climbs a tree because she's faster than the other cat and waits until I go out there and she cries and then climbs down the tree when I'm there an hour later. So that's what happens when these two cats get together. Well, what if I just put them in separate rooms and close the door? Are those two cats getting in an argument? Okay, so, and there's a reason I'm going to talk to this when I get into microsegmentation. So, somebody wants to break into my house for whatever reason, they decide to break in my house. And I tell my wife to go to the bedroom and lock the door and call the police. It's one attacker. I use my 30 years of martial arts and knock them on the ground, tie them up, lock them in a room, and wait for the police to call. Is my wife safe? Now, I locked her in a room for a reason. Because if something happened to me, I wanted the person to have to break through the door to get her before the police would be there, for example. There's a reason I would isolate this thing. So it's called microsegmentation. Did you know when they used to build buildings, they used to build these giant buildings and they had a problem that once part of the building would catch fire, the entire building would go down? Many years ago. So what changed the building code when you build a house or you build a hotel, for example? You have to make it that if one room goes down, the entire building doesn't go down. Or if one floor goes down, another building floor doesn't go down. They microsegment it. They put in special walls that are more fireproof, special metal things and things like that for a reason. So when we talk microsegmentation, we're talking about what they like to call limiting blast radius. What they mean by that is if a grenade goes off in a room, if you're in another room with a steel door, you might be safe. When a hacker gets into one thing, and here's the situation. They phished you. They somehow phished an executive at the company. They got that executive's information. They have that executive's usernames and passwords. That executive can get pretty far, can't they? They're probably allowed into a lot of systems. That's pretty dangerous. So I want to do a whole lot of things, just like those Russian dolls with the doll inside the doll, inside the doll, inside the doll, which I always thought was cool. My grandmother had them, to make sure that when you attack me in one way, you attack me with a punch this way and I go this way, I better have a counter response that's already planned and coming, or a counter defense. And that's what we're really going to talk about when we talk about microsegmentation. Now, I want you to think about what that could be. So, give you a couple of examples. Companies that are very high security might have 1,000 different VLANs or 2,000 different VLANs that can't talk to each other. How about on a cloud? You'll see a lot of cloud providers that do this. They are users of the cloud. They know the cloud's kind of risky, so what they might do is this. They might have one VPC, for example, for their web stuff. Maybe they put their web stuff over here in one VPC. Maybe they've got a finance VPC that's separate by itself. Maybe they've got an accounting VPC that can't talk to the finance VPC or the web VPC. Maybe they've got an R&D VPC, and all this stuff is kept separate from each other. They're all separate and nobody can reach each other if you don't want them to, by keeping them in separate networks. Now, watch how easy this is to break. Now, all of a sudden, we can create a hub and spoke environment with non-transitive routing, for example, where we connect to the web VPC, the finance VPC, the accounting VPC, the R&D VPC. And let's say I was using the routing protocol IBGP. Guess what? It's perfect because IBGP is non-transitive. So this hub site, for example, let's call this the hub. This hub will be able to speak to every site if it wants to, but R&D won't be able to speak to R&D won't be able to speak to accounting. Accounting won't be able to speak to finance. Finance won't be able to speak to web. This is pretty normal stuff if we used IBGP. And this is exactly what's going to happen with VPC peering on the cloud. Oh, wait, now, all of a sudden you want the web VPC to attach to this. And instead of running IBGP, you use eBGP. Or if you're on the cloud, you just change it from the traditional hub and spoke and you add a transit gateway or VPN cloud hub or something like that. Now you've got transitive routing. Poof. Now the web VPC can speak to the finance VPC. Now we enabled communications, but what did we just break? What's the trade? Nothing's free. Now Billy, Joey, and Tommy can talk to each other. Now Billy can access any one of the other ones. So we traded networking for segmentation. So to be fair, what you're really going to be deceived, everything that we do, at least as architects, is saying, okay, well, this trade was worth it. That trade wasn't. Well, we need to enable this kind of communication for business purposes. Oh, wait, now in order to enable that communication, now how do we secure it? Do you see how the security changes with transitive routing versus not transitive routing like that? The reason why is you couldn't reach it before. If you couldn't reach it, you couldn't hack it. Now you have to reach it. Now I need access lists, firewalls, and what have you. So keep that in the back of your mind. The design determines what's going to have there. So that's why we microsegment. Now let's talk a little bit about wireless. Wireless is terrifying to me. So first and foremost, if it matters, it's never on wireless. Why? Wireless, we're just sending signals out there. How many of you have ever had a CB or a ham radio? I thought they were cool. My grandfather had one. We were talking to people in Vietnam from Philadelphia. It was the coolest thing. Other times, people in Germany. I didn't speak German, but we could still hear them. It was really kind of cool. And then you'd find somebody in Canada and it was really kind of cool. Why? Because those radios were sent there. They bounced across the ionosphere. People could reach them in other parts of the world. They were radio waves. Which is harder for you to break into my building, get past my guards and plug into a port, which is hopefully locked, or tune to a radio wave. Just turn on your antenna and be there. So wireless gets a little bit tricky, and there's so many things to do. So look, I in my youthful age in network engineering, I would go to the IEEE events. So you can see they typically have a specification for wireless, which is always going to be in the right now in the 802.11 standard. I didn't make up these terms. And there's millions of 802.11 standards for various wireless things. And typically what's changed is the frequencies and the speed. We're kind of somewhere near that 802.11ax, which gets us close to about 10 gigs of speed, which sounds great in theory, but remember, it's 10 gigs of a shared media. So we can probably maximally only get 20% of that at any one time, because remember, once devices talk, they all back off. So actually, for you to think about it, let's say I wanted to minimize the number of people that are actually using a single access point in a building. I just install more access points to make sure that not too many people are ever talking to an access point at the same time. So actually, let me show you how this wireless is going to work real quick before we start talking about wireless attacks. So let's do this. Let's have a little fun with this. So this is our network back here. And by network, I mean routers and switches. What'll happen is we're going to have these little wireless access points, which are going to be little wireless radio receivers, if you will. And what we do is we plug the access points into the network. So we've got my little cat. I don't know why Cindy has to have so many iDevices, but Cindy's got a whole lot of iDevices, so she needs to come in and attach to things. So for example, here we go. Let me just put her here. Bear with me. So let's do this. This will work. So we've got this little user over here. And this particular user over here has her iPad. And what happens is she connects with her iPad. And her iPad connects her to this access point. Now, of course, she's got her iWatch, her iPhone, her iPad, and she walks through the house. And as she walks through the house, she roams from access point to access point, and then she's in my office, which is connected to, say, this access point. And that's where she's at. Now, when her computer tries to register, at least initially in my house, because I'm freakishly security obsessed, sure thing sends a challenge, and the challenge has to verify that she is who she claims to be, and her device is who she claims to be, and then she's allowed on the network. But this is kind of the way the wireless works. So these access points are where we access the network. So if this piece goes down the infrastructure, well, I hope you understand that everything would go down. Now, what happens if this access point is not what it's supposed to be? Please give me an answer. So, going back to this, give me an answer. What happens if Cindy gets sent to, if Cindy wants to go to this access point, but there's a really bad access point over here that's not my access point. And this is made by Cindy's nemesis. Cindy's enemy number one. and it's a fake access point. Now, what really happens here, and here's what Cindy's nemesis, Cindy's Emmer number one wants, is she wants Cindy when normally to connect to this page because Cindy has a habit of buying lobster and shrimp and sushi. So they want Cindy to hit this access point that is going to look like this access point and connect the credit card information and everything necessary. So when Cindy buys her next shrimp salad, salmon, who knows, whatever, this Cindy's nemesis, the cat, can now start using Cindy's credit card number, which means my credit card. So that's going to be one of the things we actually have to look for when we get here is if we get these road access points, which could be fake. The other thing is making sure we're going to have a strong encryption strategy moving forward with what we have because it is a shared media. So that's how wireless is going to work. So let's talk about some things that can actually occur. Now, with wireless, we typically broadcast the wireless address. Mike's home network. Go search your neighborhood and see how many people are broadcasting their SSID to you. And I know plenty of ill-willed people that live in cities that will look and say, oh, my neighbor's got an unsecured wireless network. I'm going to use that. And guess what? They're on their network. So, should you broadcast the SSID identifier? Well, if you don't know what it is, how are you going to connect to it? You're not. If you know what it is, it's going to be easier for you to connect to. So that's something that I want you to kind of think about that. So security by obscurity is not my favorite form of security. If I speak to my wife in Greek, assuming that's cryptography, I'm going to fail, I promise you. Somebody else in South Florida is going to be speaking Greek. So we actually have to think of what we do. Should we just count on obscurity? Probably. There's no reason for me to give you my SSIDs unless it's just to make it easy for you. Now my 90-year-old mother-in-law is coming to my house. She does not use a computer every single day. She comes into my house. How is she going to figure out how to set up wireless without the SSID being broadcast? Maybe not. So, and she's incredibly intelligent, but just doesn't work with computers. So it would be a weird thing. So we have to think convenience versus security. Now, what if we have 800 people a day call help desk because they can't get access to wireless? And in an enterprise, that could occur. So we always have to think of trades. Now, whenever we deal with wireless, we have to think about getting signals from point A to point B. Now, not everything broadcasts the signals the same way as everything. How many of you have cinder block walls at your house that are filled with cement? I do because I live in a hurricane area. Let me tell you, wireless signals don't penetrate necessarily so well. So what we typically do is we need to have some wireless network engineers come to the place, and they need to figure out where they need to put the antennas based upon the way our videos, our buildings block signals, what have you. Does that make sense? They typically call it a site survey in the engineering world. So now let's think about wireless security. The more stuff that's on wireless, the scarier it gets. Because try to come into my house and plug into the network. Probably not going to be too easy for anybody. Try to pick up the wireless signal from my 3 access points outside. Because I have to make sure that all 4 of my gyms in my house and physical therapy centers get good internet access for good music. So you're picking up, you could pick up my wireless across the street from my house. Clearly, I need some pretty good security. If I cut the signals beyond my house, can you access it? Are ways that I can block, may talk about it later, signals, radio frequency signals around me? Yeah, so we might have to do that for high security environments. Faraday cages and other things. That's a topic for another day. So the key to remember when we go to that shared medium like Cindy trying to access things, this is all shared. Everything there is shared. 100% of all of it. And that's going to be pretty important to remember, is that it is a shared medium. Which means what? It means if this cat is speaking, everything else on that access point will be able to see it. So that may not necessarily be optimal for what our situations are. So how do we fix it? Well, we use encryption. So if we now encrypt the data between Cindy and the access point, and the only way that another user, say that we've got another cat over here, let's say Sunny the cat that's on that same access point. Sunny is a beautiful orange cat, by the way. But let's say Sunny is on that same access point. All Sunny can see is Cindy's encrypted traffic. And without the decryption key, Sunny can't see Cindy's secret plans to do world domination and capture all the shrimp and salmon and tuna for herself. She really loves shrimp, salmon, and tuna, and she's pretty aggressive at going after things. So that's what I want you to kind of get out of this, of why we need encryption. Now, we've had lots of encryptions. When I started, we had web encryption. They called it wireless equivalent privacy. You can break that pretty darn quickly with a modern graphics card, so we don't use that. And then we had this Wi-Fi protected access for a little while that was kind of horrible, but it was something we used for a little while. And then we started getting into things that were a little better. We had this WPA2, and that was much stronger. It used AES encryption. And now we even have better than that, and that's WPA3 that is even better encryption, especially against brute force attacks. So we have to use encryption for our wireless. Now, initially, what we did is we used something called 802.1x. And when I first saw this protocol 802.1x, it was like I fell in love with it. And here was the reason why. No matter what we did, I did earlier in my career, every place had all these Ethernet ports in the building that you could plug into. And not being able to find, retired Navy SEALs or Force Recon Marines to stand guard over the security ports in all sides of a building, I went, wait a second, this is like a nightmare. How are we going to ever solve this? And then there was this protocol called 802.1x. And what happened is it would look at the MAC address on your computer. And what would happen is, let's say Fred, for example, wanted to use my system. When I gave Fred his computer the first time, I would enter the MAC address into a database. And that meant Fred was an authorized user. He could plug in, his MAC address was said okay, and he'd get on. Now, all of a sudden, Fred doesn't have that computer. He tried to plug in with another computer, the MAC address would be dropped. So when I first saw 802.1x, and that's all it was they called it the Extensible Authentication Protocol. I'm going to check your MAC address, and if your MAC address is listed on the allow list, you're let in. Now, that was great. It really was terrific, which is why I fell in love with it. But it ran into one problem. What if somebody impersonated Fred and did a good job looking like Fred on the way in by kind of stealing his MAC address or stealing something like that along the way? So that got us into better, more modern versions of it, like PEEP, which the Protected Extensible Authentication Protocol, which basically took those 802.1 packets and it added TLS security. So it got a little better along the way. So we have to always think about that. Now, a whole lot of these devices come with this Wi-Fi protected setup. It's like an auto wizard. We disable that every time we receive these things. We can't have auto anything. Auto everything means hack me, please. Auto means things are just open and ready to be turned on. We can't live with that. So we typically get rid of that. Now, understand with wireless devices, the antennas that we use may have a big impact on how well they perform. I am not a radio person, but if you find that kind of cool, they talk about unidirectional antennas that point towards one thing, for example, or I think they're the rubber ducky ones versus directional antennas versus things like that. Now, anything we have on the network, what happens when that has vulnerabilities? A router has some big security weaknesses on it. What's a weakness from a security perspective? Everything has a weakness. So the weakness is that weakness in the system. Everything that has a strength has a weakness. Everything. What do hackers use? The weakness. What do attackers use? The weakness. If I have a world champion kickboxer and I have two thugs to try to punch that person, those two thugs are going to be on the ground in about 3 seconds because that kickboxer's up and it's what they're trained to do. Now I take another martial art, say Brazilian Jiu-Jitsu, an incredibly effective art. Now that person's wrestling around on the ground with one person. Cannot the person defend the three thugs that have baseball bats that want to hit that person? No. And they can't do it because they're pinned to the ground. And it's too hard to get up quickly. So the reason I'm saying this is everything that we're going to be picking that I want you to think about is going to have that. So we're always going to think trades. Now, when we have these network devices, if they are hacked, we're down, right? Everything goes down. Everything goes down. That's the secret the cloud providers don't want you to know, that it's all on one network. One network goes down, all their 30 regions can potentially go down. It's all tied to the network. It's why nobody that comes from a networking perspective ever believed in a single cloud. So we have to patch the network. What about the servers while we're at it? Do we think we can leave web servers with security weaknesses or vulnerabilities on them? No. How about our IM servers? So I want you to think in terms of systems. We're always going to be patching things. Now, can we do a patch immediately? Like a consumer, like your Mac, it auto updates itself, or your Windows system auto just boots itself and updates. Do we think we can do that in the real world for an enterprise? What happens when your PC gets upgraded automatically and when you got to wake up with a blue screen? Or my Mac gets updated and all of a sudden my video broadcasting applications no longer work. So what businesses will have to do is they're going to have to look at the patches. They're going to have to test them and see if it's going to work in their system before they install them and break their entire environment down. How about the passwords to your network devices? Do you know what the most common password was on the internet when I was younger? On almost every router and switch on the entire internet? It was Cisco, Cisco. Cisco as the username and Cisco as the password. Because it was on everybody's CCI exam. On every Cisco book, they used to demonstrate username Cisco, password Cisco. So at some point, the whole internet's passwords were username Cisco, Cisco. It was hilarious. You could just log into a router. You thought it was yours, but it wasn't. And you typed Cisco, Cisco, and you got in. So please change those basic passwords that come with it. Now, here's something. Let's say you're using a Cisco access point. Let's make up a model number, Cisco 1234 access point. How do you feel about typing Cisco 123 access point as your SSID name, which it might start by default that way? Think about it. What happens if I know the model number or the vendor? Okay, so you gotta fight three martial artists. One is a jujitsu champion. Do you wrestle on the ground with that guy? If you're not a jujitsu expert, no, you have to stand up because once you go to the ground, you're done. Now, you get a kickboxer. How hard is it to hit that person? Because they're so good at not getting hit and moving around and hitting before you try. If I'm a jujitsu person, I'm going to try to get that person to the ground because I can't stand up and fight with that as a kickboxer with that jujitsu person. So when you know the vendor and you know the vendor's capabilities and you know the vendor's strength and you know the weaknesses, you know how to hack that system. Which is why those who do the most specialized training for certain things don't typically show how they train. They show the stuff that looks scary, but the real secret scary stuff is seen by no one. Because no one wants you to see how they fight ahead of time, how they defend things, how they attack things. So when we talk security, I want you to really think security global picture. Should I let addresses into my system that I don't know who they are? Oh. How many people are allowed to open your door with a key? Only the people that know you know who they are, right? Make sure you do that on your network. Is there any reason on a network to leave everybody in the same VLAN where they could all talk to each other? Don't do it. Now, someone asked earlier, and it was a really good question. How do you know when something's going on? Well, let's say you want to know if somebody broke into your house. You walk in, you open the door, and for some reason it just opens and you're a little concerned. Now you walk through the house and you're not sure, but you think a fork on the kitchen table moved a quarter of an inch, but you're not sure. Now, when you walk up the stairs, you notice a couple of little red mud spots, but you're not sure if they were there or not. Are you really sure if somebody broke into your house or not? Or you have no idea, right? Now, what happens if you had a camera system that said, person that was 6 feet two that looked like this broke into this door? After when they walked into this room, you can see that they opened this drawer. They took this thing out of this drawer. They then walked into this room, turned on the sink, then walked into this room, took these three things, and you had a log of it. How important do you think that log would actually be to determining what happened? How important is it to log what's going on in the network? Oh, how many of you think you can actually look at something that has 10,000 network devices spewing 10 log messages a second from 5,000 devices, 10,000 devices or more? It's exactly. So we're going to need at this point some systems that can actually do that. And that's going to be Siemens sort of systems. So we'll get more into that later. Now, let's talk a little bit about Bluetooth. Yeah, I like it, right? It's pretty convenient. It enables me to have some mediocre sounding music in my gym, which sounds quite good. And if otherwise, I use cables and things that make sense for things that are good. But Bluetooth is a little networking thing that runs kind of open on your phone, kind of scanning for devices all the time. Runs in your car, runs throughout your house. Now, do we think Bluetooth is typically encrypted? It's not. How often is the code to your car 0000 to connect something? My last Mercedes came with a Bluetooth connection of 0000 for the Bluetooth. I looked at this and said, how do we fix this? This is a nightmare. It's really not good to sell me technology because I'm always looking for the security weaknesses and how to fix them. So this kind of stuff is designed for personal stuff, but I want you to think about how easy is it to connect to Bluetooth? If your phone is just set to open and I just walk past you, how much information can I connect to you and walk by your side within 30 feet? See why the network gets pretty scary? So we've got the concept of adding something blue sniffing where we can start looking around and seeing what's out there, and then we can hack these devices themselves, these Bluetooth devices. So should you use a lot of Bluetooth in an industrial business? No. You're going to have to disable that stuff on the systems you have, unless you absolutely need it, because it's a security weakness. Okay. This is something kind of important. So have you ever noticed when you go to a store, there's often these little things that are stuck to the devices the things that you want to buy? Now, sadly, everything now seems to be locked behind a counter that's more than $2. I can't understand it, but maybe that's the world we've come to. But there's these little tags, and the tags tell us where something is, for example. And I used to use these RFID tags because when you would consult the hospitals, one of the things they could never find would be, say, wheelchairs or IV pumps. And as crazy as it sounds, the average nurse spends 25% of their time looking for IV pumps and other equipment. So I used to tag it with RFID things. I used to suggest it in my architectures. So here, your RFID pump is hidden under this desk where Sally hid it so she could use it when she needed it. So that's where we use RFID tags, typically speaking. So these are old devices. Now I want you to think about these, most of these tags. The power is supplied by the reader, they don't have a battery. What's the dangerous part of IoT devices and various types of tags? How easy is it to control the devices and patch the devices when they don't even have a battery in them? So I want you to understand that is what RFID is. And it uses technology called what do you call it? Near field communications. So let's think about some attacks that we have on wireless. Rogue access points. I showed you that one with Cindy, right? Where I put a bad access point, Cindy connected to the wrong access point, and she was getting hacked along the way. Now, if you go to a rogue access point, for the most part, you're not going to know. It's going to have an SSID that looks very similar. It's going to work very, very similar to what you're used to. Now, often it's at a higher power. What I mean by that is, so if any of you are familiar with frequencies and things, if this thing is coming at you from 10 watts and this thing is coming at you at 1 watt, which thing are you going to see? Which has the stronger signal? The 10-watt thing. So often, if I'm going to be trying to steal you and your stuff, what I'm going to do is I'm going to broadcast at a higher power. Does that make sense? And I'm going to use a really compelling SSID. I'm going to make it look great. And now I'm in a hotel. I broadcast a fake SSID. Users start connecting to the fake SSID, and then they log into their bank account, and I caught it. And then they log into this, and I caught it, and I log into that. Because the encryption's to me, in many cases, or at least from the wireless piece, and I can decrypt it. So keep that in the back of your mind. So how do we fix it? We use wireless intrusion detection systems that will look for these things along the way. And we constantly look for them. What does it mean for you? You are at a hotel in a conference. I'm trying to think of the place that they're like Weston has the Copley Center I used to go, though there's the Boston Copley Center I used to go to a lot. Orlando has what's that? Has this conference center that I used to go to all the time. The Moscone Center in San Francisco, where I used to go to all this time. So there's these big conference hotels. They've got access points that are like a mile long. What if you get hacked? If you attach to the wrong access point, that's a problem. But what if you set up a VPN? So I'm connecting to the wireless and I'm going to set an IPSEC connection between that and my home wireless network. Will they be able to see anything between me? No, because it's all going to be encrypted with IPSEC. So what does this mean? If you're using Wi-Fi, just encrypt your stuff at all times. If you're in the cloud, you don't own it, encrypt your things. If you're on the own it internet and you don't own it, encrypt your things. So we start migrating towards zero trust and it's encrypt everything, just encrypt everything. Because if I encrypt it and it's not Fred pretending to be Fred, I can't connect to Fred because the encryption proves that. Now, if I'm trying to send Fred the message is not going to get blocked along the way because I know what's allowed. The message doesn't get changed along the way. So use VPNs. Because there's also called the evil twin attack, and that's where basically they set up another access point and it looks just like the real thing and you connect to it and they steal your sensitive information. Man in the middle attack, same kind of concept, where you're speaking to someone and you don't know. So wireless. So remember I said that when we deal with wireless, you send and then everybody sends, those kinds of things. And what if I could kick you off of the network? So what if Chris is sitting there and he's in a big giant hotel and Chris became a hacker for the day and he created what's called the disassociation attack. And what it really did, and it's a type of DDoS attack, is he sends de-authentication frames to everybody that's using the network. And it makes them get kicked off the network. That's not that hard to do. I send something that makes all of you look like you're no longer attached to the network. And you all get kicked off. Can you use the network when you're kicked off? Is the network available to you when you're kicked off of it? If I made the network unavailable to you, that is just another form of a denial of service attack. I made the network not available, so you had access to nothing. What about jamming? Anybody familiar with the concept of frequency jammers? Was it 93.3 in Philadelphia? If any of you live in Philadelphia, I think it was WMMR. It was a classic rock station I used to listen to when I was in college in Philadelphia. Now, if that was at 93.3 megahertz, if somebody else went out there and they just broadcast loud noise at the 93.3 megahertz, it would have taken the radio station down. And I would have got the jamming. So it is totally possible to intentionally broadcast a signal to knock down somebody else's wireless signal. So we need to determine if it's coming by accident, in which case maybe use a different frequency, or is it coming from an attacker? Sometimes we will run into attacks that are just there. Now, what if when Cindy tried to log into the system and I used two-factor authentication for her, and by two-factor, the first thing was the camera that showed her face, and it made sure that her pointy ears were where they're supposed to be, her whiskers where they were supposed to be, and her mouth. So her face was recognized. And then she stuck her paw print on the computer, and that was her second form of authentication, and then she was allowed in. What if I could video record that and capture her face print and her paw print and replay it back? Then I could give it to Leo and he could access the system as Cindy. Not that he'd want to do that, but the point is that's what's called a replay attack. Now, if I replay the information back, it's there. So let's say your voice is your password. And Fred goes to the bank and he says, my voice is my password. If I record Fred's voice exactly, I could use Fred's voice saying, this is my voice is my password. So we have to really think about replay attacks and how easy they are to actually do. So keep your wireless systems updated. Make sure you use a wireless intrusion detection thing. Make sure you've got one-time authentication mechanisms to actually get on the system. I think I'm going to stop here for a few minutes for questions before we get to mobile networks, like cellular networks.
All right. So let's get right into the questions. Um, let's see, our first question is going to be from Collins here. Could you explain the difference between TLS and MTLS and when to use them?
Yeah, so if we look at transport layer security, it's a protocol that does that encryption, like I said, between the client and the server. But there's a difference in the authentication. So the server proves its identity. So Cindy the cat goes to the website, Cindy's favorite shrimp, tuna, salmon, whatever.com. And Cindy checks the certificate of the website. And that shows that Cindy to the website that it's who she claims to be, that she can use her daddy's credit card to go buy whatever she wants to buy at the cat store. Now, by comparison, when we do with MTLS or its mutual TLS, it checks the sender and receiver. So Cindy has a certificate that proves that Cindy is Cindy Gibbs and who she claims to be. And the server itself has the web server that it claims that it's Cindy's potential thing. So in this particular case, Cindy proves to the client that she's Cindy, and the website proves to Cindy that she's Cindy. So now we're more towards that zero trust of environment where we're authenticating every request. And it's not just trusting Cindy and her credit card to buy something, it's making Cindy prove that she's trusted and the website's trusted. So, Colin, that's really a great question.
All right, next question. I wonder if what is used for a key to make a hash, if that could be captured, could fake messages be hashed and sent?
Okay, so here's the thing with the hash, and I am not a mathematician. And I'm going to say that because not being a mathematician, I find hashing the coolest thing. So let's really talk about what hashing really is. I mean, this is why I find it so cool. So if we've got, let's say, the letter A, and we're sending the letter A, just for whatever example, we'll call it A. Now, when A goes into, say, a 256-bit hashing algorithm, A will always come out with this like 256-bit thing that's going to look like this. And every time A comes in, A will produce this identical thing. Now, what the coolest thing, which is why I always found this, is it's one way. So if 10 computers type in A, they're all going to get this ridiculous looking response. But you can't somehow go from this response back to the letter A. It's a one-way hash, which to me is just magically cool. So the point is this, and this is where we tend to use this hash. So the message A is sent along the line. So when the message gets here, the message gets decoded against the hash. So the hash gets seen, the pre-hash and the post-hash are seen, and we say the hashes are good. And that's how it receives the message. So that's a one-way hash. Now, there are a lot of hashing algorithms. And ultimately, when you're at the PhD mathematician level, they start looking and saying, well, which one of these hashes are secure enough so they can't be reversed engineered? And that's where you would typically get involved in hashes on the cryptographic system. And you would typically use things like salting hashes to get past that. But I am not a mathematician, but I do think it's kind of cool.
All right. So this one asks, do you need IPSEC for the VPN?
Well, realistically speaking, you can use a TLS VPN or an IPSEC VPN, or you can use both. If I needed real security, like heavy duty security, I would use TLS for the payload itself. And then I would use an IPSEC tunnel on top of that, encrypting the payload and the message, which would give me a form of double encryption. But you can use either or both. Good questions today.
The next one was specific to the little scenario that you were doing about access points. So I don't have the context. Hopefully you still have it in your brain. Are these access points faulty, misconfigured, or unauthorized, like rogue devices?
Any of the above. Usually, they're somebody who intentionally put them there. Now, why might you find a rogue access point? So, there's a couple of reasons. So, if you recall when Isaac was talking about fatigue yesterday on the first day of IM fatigue and alert fatigue, let's say you work at a company that security is so crazy and their wireless systems are so bad, you might put your own wireless access point in to make your life more convenient. Now, that is someone that means well, that's just trying to do their job because the security is too crazy, and then I opened up something. So that is one form of an access point that was done by a well-meaning person to do their job. I didn't say it was okay. Lots of time a hacker will come in and they will put in those route access points to actually capture information. And why might they do it? So let's look at two different scenarios. And have any of you seen the movies Ocean 8, Ocean's 11, or any of these complicated crime movies? Because I want you to think this way as a hacker. So the one thing might be here, it's just an opportunistic thing. We've got 50,000 Cisco people in the Moscone Center in San Francisco. We're going to put up a bunch of wireless access points and capture as much as we can of Cisco people's credit cards. That could be one. Now, option two would be if I wanted to execute a serious hack, I'm not going to be able to do it in a single day. So I'm going to send some people to scope out the building. I'm going to try to sniff some usernames and passwords from some access points. I'm going to send some phishing links and I'm going to start collecting a lot of data. I'm going to try to map out the network, maybe potentially test some tools to figure out where their weaknesses are. And then when I know exactly what I'm dealing with and exactly what my assets are, then I launch my attack. So it all depends what they're using. It could be part of a deep, serious thing. Like I say, the movies Ocean's 11, where we need to do this before we can do this and have access to this and have access to this because you're doing like one of those Mission Impossible things. Or it could be simply, let me just steal your credit card numbers. And a lot of times it's just that. Most hackers aren't that sophisticated, but there are some that are very sophisticated.
All right. The next one is how secure are the RFID microchips in e-passports?
I would carry something to protect them. So, like in my wallet, for example, I carry two different things. I know, I'm security obsessed. I have an RFID shielded wallet that blocks RFID shielded things. And I also have one of those RFID jammers where it sends out RFID signals to block other signals from being there. So that's what I typically do. So I would do something like that for my passport along the way as well.
All right. Next one is asking if you can say something about end-to-end encryption and its cost and deployment complexity compared to VPN.
Well, I'm not exactly sure by what you mean end to end because there's multiple kinds of encryption that we're actually talking about. So to run an IPSEC tunnel between two units costs absolutely zero. Now, what does encryption cost? So there always is a cost for everything. So let's talk about where your typical costs are and the way we work around it. So if I'm users over here, and this could be across my, and my users over here, and I've got another user over here, and I own the network from point A to point B, and I want to create an IPsec tunnel between these two computers, there's no cost other than using my internet access. Now, here is the cost. In this device itself, it has a CPU on it. And when you start sending packets or anything to the CPU for encryption, it takes a lot of load from the CPU. So ultimately, we're limiting the performance of this device, or we need a bigger device with a more CPU. So depending upon that type of cost. Now, depending upon what we're needing and what we're encrypting, we might also use a hardware device, for example, that does the encryption on both sides of things, and that would alleviate the encryption here. So there's nothing to be done. But there's really no cost for that. None. And it's completely secure. Nobody could even tell that these two people are speaking. Now, when we start thinking other environments. And what I mean by this, what does it take to get to real cost? And it's real knowledge of what's going on. So what are we really doing? You know, if it's me, every time I've got one server speaking to another server inside of my systems, this is encrypted. Now, if it's possible, and say this is the CPU, and there's going to be a cost to this specifically in terms of compute performance. But what I might do here is, let's say this is the server itself, and I've got another server and a server. I might actually do what's called homomorphic encryption, where I'm encrypting what's in the DRAM on the way to the CPU. Now, again, no cost for it, but it's going to limit the number of, it's going to take CPU resources, so you won't be, the server won't scale as well. So potentially I need more scars. Now, the hard drives themselves, I'm going to encrypt data here, realistically speaking, on the storage. I'm going to encrypt the storage too. Now, depending upon my storage, I'm either going to have hardware encryptors that do it with no penalty, so there may or may not be a speed or a penalty here. And then I'm going to basically encrypt going through this network anyway. I'm still going to use IPSEC. So there's really not a lot of cost that's associated with encryption other than the computational effort of it, which might make you need more things. Now, where does it cost? Now, if I've got encryption everywhere in my system, where's my cost? Well, I have to have people that are smart enough to understand the encryption, where the encryption is, and how to troubleshoot with encryption. So I need smarter people. So whenever I have more complexity, I have to pay more for smarter people. And realistically speaking, that's realistically what I'm typically coming from and typically doing.
All right. What would you prefer? ZTNA or VPN or other alternatives standards for of VPN like SASE? What is for you the future?
So Daniel, I want you to think about it a different way. What is the surgery you would like to have? What pill should I prescribe you? Should I give you Lipitor, atorvastatin? Now, why am I saying this? If your lipid profile is perfect and you have no cardiovascular risk profiles, there's no reason I would prescribe you atorvastatin. None. Now, if you don't need surgery, I'm not going to give you surgery just because I can't. So in every environment, in 100% of businesses, I have to look at what those business needs are. I have to look at what those business pain points are. And I have to look at what those business challenges are. Who needs to speak to whom, at what performance level they speak to whom. And then I make a diagnosis and then I make it. So the key here is to remember that you should never have a preferred form of anything. The second you do, you become like a doctor that recommends that everybody gets gallbladder surgery, whether they need it or not. The key to being a trusted advisor is to look at every client, understand their needs, and choose it. There are clients now that I recommend mainframes for, and I am not joking because they still do the best job. There are clients that I say, you got to get off the cloud. It's costing you 4 times more than you spent, and your performance is terrible. There are other people that don't have the sophistication to manage their systems, and I've got to migrate them to 2 different clouds. So it all depends what they need. It's all based upon the business needs, but I don't have any preferences, and I recommend you not either. And it's going to take a little bit of all of it based upon what the business's goals are. Good question, though.
Right. Let's get back to the content.
Okay. So let's have more fun with networks. So let's talk a little bit about mobile phone technology. So we now have all kinds of devices that are powered by, say, 5G wireless networks. Now, I want you to understand your mobile phone is not necessarily the most secure device. Your communications, typically speaking, are encrypted between you and the tower. So the way these things kind of work is, to put it into context, so let's say you're trying to do something like this. And here's the way these work. So let's say you are here. in your house. So I've been meaning to get Cindy a cell phone because sometimes she comes out too late and I can't find her. So I'm trying to hope that she can call me and say, Daddy, I found a mouse. I'm going to be late. So and this is going to be Cindy's phone. Not really working real well on those manners yet, but I'm still working on that. So Cindy's phone connects to a tower. And the tower, typically speaking, connects to a phone switch. And that connects to the public phone network. So Cindy decides to call my mother-in-law, who's fantastic in every way. I'm really blessed that way. And Cindy decides to call my mother-in-law, Maria, because Cindy wants her to make her lobster, and she is such an incredible cook. So what ultimately happens is, and here's the thing to remember, Cindy's phone calls the tower, gets connected to the tower. Now, the conversation between Cindy and this tower is encrypted. So hopefully that means that someone sitting next to Cindy can't understand Cindy's conversation. So they shouldn't be able to understand that because that part is encrypted. Now, once the phone call hits the tower, it is no longer encrypted for the rest of its journey across the phone network to my mother-in-law's house in Northeast Philadelphia. So this part is all unencrypted. This is encrypted. This is not unencrypted, which realistically means other people could potentially spy on the phone call. So we think that's a great thing. No, so if you needed it for heavy use, you typically want to make sure that you use encryption. So think about the data between your phone and that tower, or the text message that you send from your phone and that tower. Your text message is not secure, by the way. Your Apple iMessage was very secure because it used an incredible encryption thing until a terrorist used an iPhone and the US government sent it overseas to have some security experts break the encryption on your iPhone. And now the US government can now decrypt an iMessage, just like they can decrypt a WhatsApp message. But the point is, anytime you send anything, you're using some form of encryption, especially if people could potentially interact things. So whenever you're there, just use a VPN. Now, let's talk about ways we can segment the network. And then I'll talk a little bit about content delivery networks. And let's talk a little bit about internal networks and external networks. So first, I'm going to show you the worst case scenario. Let's say you all have this in a single building. Now, this is what not to do now. Most people do this in cloud computing, which is insane. But then we wonder why so many people are getting hacked when they're using the cloud. This is what you would not do. So I wouldn't let people in to use the internet inside of my building. I wouldn't let the web stuff be here. And then I would not let let's say this is the drug company and it's the secret formulas for new drugs. And over here, I've got my finance stuff. I've got clinical trial stuff over here going on, which is probably some really serious stuff. You don't want that information getting out. Now I've got sales and marketing plans of which doctors we bring and give which gifts to get them to hopefully prescribe stuff. So I've got the sales reps and their business of what they do. So let's say these are the divisions of it. Now, would you ever be crazy enough to put them all in a single building where here you have to go from the internet into my account to the web, and while you're at it, you can steal my secret formulas? I mean, this is insane. This is not what people ever did before, and a lot of people are doing this in cloud computing, and they're just saying, "Oh, well, this is fine." Now, let's think about how we could do this differently. What if we put the web stuff by itself? Now, is this a lot safer? Nobody from the outside world is ever allowed into our inside world, and now we only have our private stuff. Now, what if we did this? What if we put access control lists between these device subnets so that none of these subnets can talk to each other with ACLs? Now, it's really important for the sales reps to not speak to the clinical trials people. So instead of, in addition to just putting an ACL, I'm going to put a firewall to block it. Let's kind of put some of these pieces together to kind of show you what it would look like for real. And this, again, this applies to any data center, any cloud. It really makes no difference. So let's create one more. So you can think about how we can do this. So let's say that we've got subnet 1, finance. Subnet 2 is accounting. These are on 2 separate VLANs. Can they speak to each other at all? No, they cannot. Now, when we put a router up, can I also put an access control list between them just in case somebody did something stupid to make sure that they can't speak to each other? Now, in this subnet, I've got a load balancer. Here, let's have some fun with it. So I've got this load balancer, which has a single IP address for all these servers in here. And now I have a virtual machine behind here. Am I going to let any traffic I want hit this load balancer? Any traffic from anywhere? No. So I'm going to tell this load balancer you can only serve traffic to a certain thing. So I'm going to put an ACL or a firewall. I'm just going to call it a firewall rule right now, because it could be either, on this thing. And I'm going to only say only one subnet is even allowed to talk to this load balancer. On these devices themselves, can I put a host-based firewall on them? AWS gives you something like a security group, but can I put a firewall on it also? Linux has, say, IP tables. And for all of this so far, especially if I use the host-based firewalls that come with the servers themselves. Guess how much I spent? People time. Nothing. And you can add an access list, which is a firewall rule for the most part in any router in the entire world. So I spent almost nothing. So everything was internal and protected. We used ACLs here before, so we determined who could speak to whom. We used Active Directory and other forms of IAM, just like we always did. And then here was the internet. Here was our firewall. And if we had a web server, we created a DMZ outside the firewall that could reach the web server. So what's this going to look like? So what we have in this situation is internal devices will be able to go out to the internet and their traffic will be allowed to come back. but nothing from the internet ever will be ever allowed in to this network. Now, what we will do is we will create an environment where the firewall will say TCP traffic destined to port 443 for this web server will be allowed in. So that's really what we're talking. This is old environment. It's much harder to penetrate this than it is in a cloud computing environment. This is much different. So these are going to be here everywhere, and this is not just going to be done on some device, it's going to be done everywhere. The servers, the network devices. So going to be a lot of places and a lot of people are going to have to touch many of these points. But that's what we're typically dealing about. So what would this really look like? And what are we typically talking about? So here's what it looks like. And I'll get to the next thing next. Like, how would you secure a web server? Well, we're going to use a lot of different things. So if I keep that web server outside of my systems, if you hack into the web server, can you hack into me if it's outside my firewall? Okay, I left the keys in my car outside my house, and it only has the keys to my Mercedes. Can you get into my house? Because I also have the, what do you call it? I have the garage door opener disabled because I always viewed that as a security problem. So can you get into my house with only my car key? No, you could take a nice ride and get massages in some massage seats, but you're not going anywhere. You're not going far because you don't have the key. Because that Mercedes is outside my home. Same thing with the firewall. You attacked it outside the firewall, you got a problem. Now, I keep my car inside the house and I can leave my door open and the keys in the car. Now, is that seriously a threat to my car and me and my family? It sure is, because you have full access inside my home. So anybody that's crazy enough to put their web stuff in the same VPC or VNet as their other cloud stuff, just expect them to be hacked. And it's just a matter of when, and I see it every day. So think about where you do it. So what's it going to really look like? I want you to see how many pieces of protection it's going to take to protect a web server. So web servers outside of our network, not inside, right? Today, does anybody remember that conversation I talked about where I can send a web server 50,000 SYNs and it has 50,000 open connections and it's going to crash because it can't handle anymore? Does anybody remember that conversation? So what if there was this magical device that could sit out there, that could look at the traffic before it gets to my server and says, don't send to Mike. It's too dangerous. Well, that would help reduce my risk of a distributed denial of service attack by a lot, right? Don't send me the bad stuff. Now, the thing that we typically use for that is something called the content delivery network. And content delivery networks typically do two things. One is they cache content, which is super cool. And if we had more time to talk about it, I'd talk about it. But I could talk about that for more time than just the 5 sessions that we have here. But we use a content delivery network. So because that will, in many cases, have a DDoS service like Cloudflare, which is the largest DDoS provider in the world, or the cloud provider that has their own small things like AWS's CloudFront is a small CDN compared to, say, Akamai. But they've got their shield. Akamai's got their thing. Cloudflare blocked the largest DDoS attack in the world on their CDN. So I naturally think, and I know, and I'm going to draw it this way because I naturally think this direction in the way I think of movement from the right side of the screen to the left side of the screen. So work with me from right to left because that's usually the way my brain processes things. So the way we would protect that web server is to say at the outside of our network, we use this content delivery network. What's it for, everybody? What's the CDN for? Well, for caching, for one thing. So I get 100,000 web requests for my web page. I serve it once, and the cache kind of pushes it out. So that helps me in one way. But any bad traffic doesn't come to me in the first place. So don't send me the bad stuff. I'm semi-protected, right? Now, is that enough to protect me? Absolutely not. It might stop a little, but it's nothing. So what do I need to do to make sure that my legitimate traffic can get out and come back, but nobody bad can come in? Well, if I put a giant wall around my house that was 100 meters tall of cement, how many people are going to climb 100 meters of a slick cement wall to get into my house? Not many, right? And if so, they're going to be like an Olympic level climber. And it's probably not going to be worth it for them to do it because it's not going to be worth it for them. So that's what we're typically going to do. We're going to put a giant wall around our house. The Great Wall of China. It's a firewall. We just called it different things. So typically speaking, in a data center, we're going to have a set of firewalls here. Now, in my data center, I might have these two firewalls doing their thing, and fire A and well, A and B are high availability devices, multiple power supplies, multiple this, multiple that. Now, if I go get a firewall in a cloud provider, for example, is it going to be on a $100,000 device, which has got multiple power supplies and all these hard cards, or is it going to sit on a virtual machine? It's going to sit on a virtual machine, so it's not purpose-built hardware. So, for those of you that don't know, in network architecture, cloud architecture, high availability architecture, anytime we want security and we want to use more than one, we want to be able to load share with a couple of devices. So if I've got three firewalls and one dies, I still got two left over, right? So how do we do that? We've got these things called load balancers, which will enable us to share the load across 3 to 50 firewalls. And if one goes down, it doesn't matter, it'll share the load. So typically speaking, and we're going to use a load balancer before a firewall, especially in the cloud computing environment. And it's typically going to be something like a network load balancer because we're looking for speed here. And this is going to be a firewall. Now, I want you to see the difference between a modern firewall and a cloud provider's basic firewall, because you're going to be using a modern firewall. And that's why in many cases, I really hate some of these cloud provider certifications because you can't use most of their stuff for these reasons. So here's what these new firewalls are going to do. And they're called next generation firewalls. So here's what firewalls always did. And this is the way a firewall always did. So we had the firewall here. And we had my pretty little child Cindy, if let me get a photo of her so if I can. So we've got my pretty little girl Cindy. I'll take it from when she was an actual little computer, when she was writing when she was a little kid and when she was helping me write a test for something. I don't know, that's probably not a good example. So let me find this cute little computer. When she did help me write a book at one point. So we've got this little kid and she wants to go out the firewall. Isn't she beautiful? I adopted this cat for my wife, and the next thing I realized, it's like, so C wants to go to the internet. And here's her shrimp and lobster place that she wants to go to. My cat's got expensive taste. I wish I could stop it, but whatever. She's too spoiled. I got to take leadership training from my cat. She gets everything she wants every time. So the way this works is Cindy goes to the firewall to go to the shrimp and lobster webpage. Now, when Cindy's packet hits the firewall says, oh, it's coming from cute little Cindy. It's going to the shrimp and lobster, and it creates a table or state. Now, when shrimp and lobster's response goes back to Cisco, it hits the firewall. The firewall looks at it and said, it's shrimp and lobster responding to Cindy, and the connection was initiated by Cindy to let it in. Now, anybody else wants to come in, they are not allowed. All firewalls do this. All of them. Now, here's the difference between the cloud providers' firewalls and the real industrial firewalls that you will use. Now, out of nowhere, this firewall notices something that looks really, really bad. In fact, this firewall notices that there's 1,000 wolves that want to get in to talk to Cindy. And this firewall hears the wolves howling. It looks at him, it sees him, and it says, Cindy should not be allowing wolves. And it sees something that scares the firewall, and the firewall says, wolves, you're not allowed. I'm blocking up a new address, and this thing keep you from getting near me. So that's called behavioral anomaly detection. And that's the way the best firewalls work from our firewall vendors, Cisco, Palo Alto, Checkpoint, Fortinet, is they look around and they see what's going on. Here's the weakness in your cloud provider. The thousand wolves come. Now, this firewall, if it's not like the cloud provider, sees the thousand wolves and says, well, they're just a thousand wolves. The thousand wolves have never, I don't know anything about wolves being dangerous. And then the wolves find a way to break through the firewall and eat Cindy. That's why you typically can't afford to use the cloud provider's weak firewalls, because it doesn't have the capability to say something looks like a threat. So keep that in mind. If you take a cloud provider certification, they want to get you all excited about that stuff. It's probably why you can't use it. So keep that in mind. So we had one layer of firewalls. Now, how many of you are martial artists like me? Alonzo, Steve Chamberlain. Every martial art has its strength and weakness. My first martial art said you can never be on the ground for more than 6 seconds because your attackers will get you. So guess what? In that martial art, we learned how to stand up. Now, I realize that a lot of people like to attack you with knives, right? So, who teaches the best knife fighting in the world? The Filipinos and the Indonesians, with either Eskrima, Kali, or Salat. So I wanted to learn how to use a blade, so I learned some from the Indonesians and some from Filipinos. Now I realize that it's great to say don't go to the ground and get up from the ground in 6 seconds, but what happens when you get kicked to the ground? Well, so I studied some Brazilian Jiu-Jitsu. And by doing this, I constantly figured if one thing failed, another thing failed. Does that make sense why a good mixed martial artist studies more than one martial art? Because Hoist Gracie is fine until he gets hit by someone that can throw a great punch and then gets knocked out or choked out by Matt Hughes because it's a different skill. At a certain point, you need more than one. So because of that, do we think that one firewall type of firewalls is ever going to be enough for a high security environment? No. Because now I just got kicked to the ground and I need jujitsu. So typically speaking, every firewall, every weapon, every defense, every car has its strengths, has its weaknesses. My SUV feels great on my back, but I promise you it's not fast like a Porsche. Couldn't be. Weighs like 6,000 pounds. Everything is a trade. So we want to think about that. So if it matters, chances are you're going to use another set of next generation firewalls. You have to. Now, a couple things are going to happen. Do we think that this firewall is going to give us a lot of logs? If any of you have ever seen firewalls of packets that are done, allowed, rejected, I mean, this could fill up things that like 1,000-page libraries in a matter of a week. How about this firewall? Now, even though these devices can spot an intrusion and stop them, wouldn't it be better if I have more devices that do that? So typically speaking, I probably have another set of network load balancers and some IDS IPS systems, which are on the firewalls, but not from a logging perspective. I'm going to get more here. And what are these devices going to do? They're going to look and monitor the system. And if they find something, they'll both alert me of it and they can potentially stop it in real time. So if this is let's say over here, this is going to be the web server. We have a load balancer, right? It's going to front out these things. So if this is the website's IP address, let's say for argument, the website's address is 1.2.3.4:443 or port 443. Does this web server need to allow anything other than Traffic destined, TCP traffic destined to port 443? No. So the firewalls are going to block it. These things are going to block it. These things. Now, this is the load balancer, which typically has an external website. Can I now put some type of specific web application firewall directly on the load balancer that's going to look for web exploits like SQL injection attacks to further protect the thing? I'm going to. Now, the reason I'm trying to show you, and this is just a network security piece, it's going to take so much more. These servers themselves, do they come out of the box hardened? No. Your computer comes out of the box the most insecure as possible. So if this is a virtual machine, it could be a container. I don't care because this architecture is fairly similar. I have to lock these systems down. What happens if these things get a worm or a virus or malware? Is that a problem? Yeah. What happens if this firewall fails? This firewall fails, this IPS system fails, and this web application firewall falls here. Should we also have a firewall on this device that only allows that one type of traffic in? So we're going to put a lot here, like some host-based firewalls, some anti-malware kind of stuff. And of course, we need to send all these logs to some AI-enabled SIEM and source systems that can say, hey, we got a problem, let's do something with it. That's kind of how we would protect a web app. But look what we really did. If you really think about it, don't let the bad traffic hit us. Don't let anything go in except what's supposed to. Don't let anything that goes in what's supposed to. Don't let anything that goes in what's supposed to. Block everything that you're not supposed to, and then block it all here. And then monitor everything that goes here. Now, that you think we're not going to use IAM? Of course we are. Now that you finally reached my door, I'm going to determine who you are and what you're allowed to do. But do we see how these pieces and parts kind of fit together? So let me cover a little more on networking for a few more minutes, and then I'll take some questions for the day. And then I hope you understand why I kind of went down the path of showing you what these basic networking things before we got there. So let's talk about what may be one of the most confused and scariest things that I've ever seen people do in networking, especially cloud networking. And I'm going to show you how this could be used intelligently and how people use this to get hacked every day of the week. So let's talk about the concept of a jump host, and let's talk about where it came from and why it was such a good security thing and how people turned this great security thing into the way to get hacked. In fact, it was so bad, and they were teaching it in AWS certifications and Azure certifications, that the cloud providers had to make up something they called their own Bastion host or remote access service. And why do they do it? Because they knew the people were going to get themselves hacked every single day by the stupidity of their Bastion host. So let's talk about a smart Bastion host, and let's talk about how you get hacked with a Bastion host. Because they're not the same. They're two different things, this concept of a jump host. So this is a smart jump host. And this is where it used to come from. Now, it came from, let's say you are here. Let's say you are in the main campus. And all your, say, people that were your network engineers were on the 172.168.1.0/22. Everybody that we had was coming from a tech perspective that would ever come in. And then let's say we had the remote campus. And this is the remote campus. Let me change the color of this so you'll see where it used to be very safe until people went a little cuckoo. Now I want to turn this into a red over here, and then let me get rid of the fill. So under those circumstances, let's just change the color of that text so you can see it. And we had this jump host over here, and I'll show you what we had actually over here. And then the jump host enables you to connect to the rest of the network. Now, here was the way this used to work. One is you had a direct wire between these two campuses. So this was your main campus and this was your secondary campus. This was remote campus. Now, this itself was a private line, so this was a wire between you and them. Now, we would pop this host here, and this would be a jump host. And these things were so tightened down that set, and the way we created it was this, that you had to be coming from this subnet, because if you weren't coming from this subnet, you would never be allowed to touch the jump host or even cross the link intentionally. Then when you got to the subnet, this jump host would, because it was on a private network, would verify that you are who you claim to be with your IAM, that you were coming from the right host. And then from there, this would be the only address they could reach anything on the internal network. So this was secure. Why? This was a private line. This was not on the internet. So I want to make it clear to you. It's like you having a wire between your house and your brother's house on that wire. So if you have a wire between your house and your brother's house, it's fairly safe, right? Your wire, you own it. Now, here's where people took it to the wrong way. Now, I had to be approached here. Now, this is what people started doing, and the cloud providers knew they were going to hack. That's why Azure made a Bastion host service, which wasn't a Bastion host at all. And AWS just created their own remote access thing. This was what they would do. Now, I want you to tell me how it's going to get hacked. They would stick a Windows or Linux machine here like a crazy person on the middle of the internet. Now, this internet, which was completely unprotected, has this unprotected server. And then this unprotected server had a network card going back into your VPC. So it had two network cards, and that was all attached to the private network. So all any hacker had to do was get access to this unprotected Bastion host, and they had a full backdoor into managing or hacking every system you possibly had. Does everybody see how dangerous this is? Please raise your hand so I understand that you see how dangerous this is. Now, if we had to go to this level of effort, I want to go back to that web server. I want you to see it. Raise that hand. I want to know that you see it. Remember what we did to protect a web server. This is what we had to do to create a web server, just for that web server to be secure. So we would never leave any server out there open. We took 3 firewalls, IDS, IPS system, a 4th firewall, and then hardened this stuff. And that is the exact opposite of just sticking something in there with a backdoor. Now, going from your private system to your private system was a totally different environment. So I want to make sure everybody gets that. It looks like everybody got it. Good. So we talked about firewalls. Now let's talk about proxy servers, which we may use for security, especially in high security environments. Here's what a proxy is. I connect to somebody or something else and they do the job for me. That's what a proxy is. A proxy vote is this. I sign my form and I give it to somebody else and they vote on my behalf. That is the proxy. So what if you wanted to control how people could go to the internet and where they would go? How many of you live outside the United States? How many of you live in the Middle East, for example? In some countries, you're not allowed to access certain things. Now, when I started working, companies were real smart. Internet access was really expensive, and they didn't want their employees shopping all day on eBay, on Amazon, and on barnesandnoble.com. And I remember I was trying to do my CCA, and I was trying to buy some books, and I couldn't buy them. Why couldn't I buy them? Because the company wouldn't let me go and buy them during work time because they wanted me to work. So, what is a proxy server? And I want you to see how it's used from the perspective of security. Let me draw one. So, I've got, let's say, 10,000 users over here. And I'll show you where this is very common. I don't let these users ever go to the internet ever. So I have these users connect to a proxy. Let's say they want to go to Go Cloud Careers. So the users connect, they hit the proxy. The proxy goes to this website, www.gocloudcareers.com. The proxy then sends the proxy then sends the message. The proxy goes to the internet, collects that. Now the proxy sends it back to the user that requested it. Now, somebody else at that same company wants to become a security architect, so they go hit that proxy. The proxy caches the information and sends it back to them. So that's a proxy server. So what's going on is this is the device that connects to the internet, and none of these devices ever connect to the internet directly. Now, let's talk about where these were widely used initially. When I started the internet, a 45 megabit per second T3 in the United States was about $50,000 a month to connect to the internet. Now, of course, I've got a gigabit at home that's $100 a month now, but 50 grand a month for 45 megabits per second. Now, me and 10 other people were actually trying to access the same web page at the same time. Should I send it all to the internet at the same time or send it once, cache it, and send the data back? So that's where proxy server started. Here's the second place proxy server started. If you run a bank, do you want your employees doing stupid things and illicit things at work, like spying on your competitors? Or going to websites buying pictures of people that are undressed, for example? Or going and buying pictures of who knows what some kind of weird thing could be? You don't want that. That's a security risk for you, right? Now, do you want your employees all on Facebook all day long? Or do you want them working? I can tell you they had to keep me off of the fitness websites because if there was anything related to workouts, performance, nutrition, anti-aging medicine, I was on it all day. So they had everybody needs something to be filtered out. So that was the concept of the proxy server when I started. Now, there are parts of the world where people are not allowed to access certain things. For example, let's say you live in the Middle East. There are certain things that are considered illicit and inappropriate that you're not allowed to see in certain countries. I'm not here to say right, wrong, or indifferent. I'm just saying that's what it is. So what these countries actually do is they use a proxy server. And what they do is, for example, they do this. 10,000 users want to go here. So 10,000 users go to the website. They want to go to Amazon.com, buy a book. They're allowed to buy a book. The proxy server sends them home. The user wants to access this, then they're sent home. Now the user wants to go to a website, say it's filled with porn or whatever. The proxy server says not allowed, and it sends a message, you can't access this site. It's been deemed illegal, inappropriate, or what have you. Again, not here to judge what's right or wrong. I'm just saying that's typically where these proxy servers are used. And they're used widely for that security things. Now, from an employer's perspective, I think it would make sense where you don't want people doing certain things that could get you in trouble on the job. And that's realistically speaking what we were talking about in terms of proxy servers and their use in security. All right, that's kind of where I wanted to end today. So let me open it up for questions for the rest of the day.
All right. And while we wait for questions to come in, Mike, can you let us know what we might have in store in the next session?
Oh, yeah. So And I haven't gotten through the schedule exactly myself because I was under the weather and wanted to tune the format that we do it. But we've covered the two biggest elements so far, which are network security and identity. So that's going to leave us with things like application security. That's going to leave us with data security. That's going to leave us with physical security. And that's going to leave us with the other security domains, which I think you're going to find fun as well. So that's realistically what we're speaking. We will probably get to, we may do physical. Well, actually, which do you want to hear from next? Physical security or application security?
Yeah, let us know in the chat box. Just type in physical or application, and we'll see which one wins out. You can't say both. That doesn't count. All right. So while we wait for those to come in, um, I'm not quite sure I understand this question, but of course I'm not you, Mike. So maybe you'll understand it. So it's, can you add a firewall rule without a firewall?
So almost every device in this point has the ability to add here's what a firewall rule really is. It says, look, it looks at the source and the destination. So remember I went to the header and said it's got the source and destination. So source is Mike, destination is Chris. Protocol is TCP or UDP, and the port number is, as for example, I want to connect to Chris's web server, which is TCP port 443 SSH. So for the most part, the routers I have will enable me to create an access control rule, which is not going to be stateful, but it's going to serve the same function as a firewall rule would do. So I can typically do that on a layer 3 switch. I can typically also do it. Now, on your server themselves, most servers themselves enable you to add a firewall rule. I think it's Ubuntu uses something called the UFW firewall. Red Hat used to use the IP tables firewall. I think it still does, but I'm not completely sure. Any Linux people, feel free to put it in there. I'm not really a Linux user. I've been an architect, not an engineer, so I don't get to touch the tech for the most part. But that's realistically speaking what we're talking about.
All right. So next one, in your diagram, is there a link between the proxy slash cache and the internet to your website to retrieve the information? What
Uh,
bandwidth would you recommend between them?
So whatever internet connection is there, and bandwidth is determined by the load and the number of users. So I will have obviously something different if 50,000 users needed to use it than 5 users. So I always need to know what I'm actually using. And I also need to know the type of bandwidth per user. So I've got some users that send email. They don't need a lot. And I might have a video editor that's pushing a terabyte of data that's stored per day, and that might mean that person needs a 10 gig link or a 5 gig link. So it always determines on the number of users and the type of data they're working with.
All right. Next one. Could you please explain the concept of a reverse proxy and how it works?
Absolutely. So that's a great question. So a reverse proxy is effectively like a load balancer. And I'll show you what I mean by that. So let's create a new slide, which, oops. So let's say I've got, this is my load balancer, and I've got 5 web servers. And I'm going to, and then I'll show you the difference between this and a reverse proxy. But it's important to understand what the load balancer is first. So the way a load balancer is it's going to have one IP address for all of these public facing servers that's going to be here. And what'll happen is the packet will hit the load balancer, and the load balancer will say, send the data to this web server. This web server responds. The next time it hits the load balancer, it sends it to this web virtual machine. This one responds. The next time it sends it to this virtual machine, this one responds. And it can do that on a latency basis. And why are we using this? For 2 reasons. One, If we lose one virtual machine, we're still good because we still have two others. So the load balancer increases our availability by eliminating single points of failure. And we might need to use multiple load balancers in the data center to replace this device logically. And it enhances the performance because if I can have 50 servers, it's better than one server. So that's where we use a load balancer. So packet comes in, load balancer forwards it. Now, a reverse proxy is a load balancer. It just does one thing different. So it caches as well. So let's say the first time the request hit this web server, and then the web server responds as the reverse proxy caches it. Now, the second time the same request comes in that the previous web server hits, so it hits the reverse proxy and the reverse proxy answers. Now, the next time it's a new request that the proxy hasn't seen before, it gets sent to this web system. And now the next time the user tries to set the same one and it gets responded by this. So a reverse proxy is a load balancer with caching. That's really a great question. That's a reverse proxy.
All right. So our next question says, I'm confused now. Is access control list a firewall?
So here's the thing. An access control list and a firewall rule are identical. The only question is the level of capabilities of the device that's looking at it. So here we've got an IP packet. You know what? Let me go. I'm going to actually get you a Wikipedia packet header because I think it's going to help. So IP packet. Let's get a public header that I can show you. IP packet header. I want to get so because I mean I kind of drew my own little thing, but here this is Wikipedia. This is free. We can use this. It's public domain. So let me go back to this. And we try to expand this as much as I can so you can see it. So this is what a IP packet.
Part of it is off of our screen, Mike.
Okay.
Like we can't like.
Yeah, I gotcha. Yeah. So what are we really looking at when this comes in? And this is what the routers look at and the firewalls look at. So this is the version of IP we're using, like IPv4, v6, what have you. This is a type of service which we can use to create quality of service. This is the amount of stuff that's in the packet. This is the time to live, which is it gets degraded by every router. This is the protocol like TCP or UDP. This is the source address. This is the destination address, and this is the protocol. So if we create a rule on a router that says allow any source address to connect to the destination address 192.168.1.1 port 443, what'll happen is the access list will allow any piece of data that goes inside of this to go through. And it really makes no difference whether it is a router connecting to another router that has this, or if this device is not a router and it has a firewall in between it, that same rule is going to be looked at in exactly the same way.
Your chart went off the screen, Mike.
Oh, that was intentional. So the point to remember is whether this is a firewall or whether this is a router, that access list is identical. So there's no difference. Now, what is the difference between that? The router itself is actually looking at the packet itself and saying, does it have the right source of destination address going to the right destination address protocol and port number? And it's going to look at that. And if it's allowed, yes, it'll be sent, and no. So that is a firewall rule. Now, when we get to the router, to the firewall itself, what it's going to be doing is it might get a little deeper. And what I mean by this is if this is a firewall, a modern firewall, in addition to just looking at this header, which a traditional firewall like the ones you get from your cloud providers do just that. They just look at these headers for the most part. But now this new firewall, if we're dealing with a sophisticated firewall, a separate and it like a layer 7 firewall can look deeper into this. So it can look into the header of the packet. It can look at way if the thing is behaving properly. It can actually look at the application itself and make sure the messages are the same, application traffic. So the firewall has more sophistication to look at beyond the simple firewall rule of that allow this source address and destination address. But the access list firewall rule and the firewall are blocking on exactly the same way in exactly the same manner. So every layer 3 switch in our network has access control lists, which are basically like firewall rules, but it's not that deep packet stateful infection. It's just looking at the headers. That's a great question.
All right. So our last question is going to be, can a content delivery, dev can CDN play double duty by acting as a proxy server too?
Well, no, but it does do caching. So the key to remember is a proxy server does caching on the way out. So I am not allowed to go to the internet, but Chris is. So everybody in my company goes to Chris. Chris goes out, fetches what they want, and gives them back. That's a proxy server. It does it for you. In that reverse proxy, what was it doing? It was doing load balancing, but also caching. So what is it that a CDN actually does? Well, it actually does caching and it determines when you're allowed. So let's kind of look at anybody ever seen what an internet point of presence looks like? It's kind of cool. So let's just draw one. So here's what the way the internet works. There's going to be these buildings called point of presences, and they're all in over the place. And depending upon the CDN, if you were to go to Akamai, for example, I think they have like 5,000 locations for these caching systems. Where if it's like AWS, it's a couple of hundred, like 600 or 700. So they're not all equal in terms of size and scale of CDN. So what happens? You've got this point of presence, and here's what happens. And this is the way internet routing works. So in here, what we do is we've got wide area network coming in. So let's say NTT brought a connection in from Japan. And let's say Etisalat in UAE has a connection in. And let's say we've got Telefonica in Spain. Let's say we've got some people in the Caribbean using cable and wireless, Caribbean and Central and South America. Let's say we've got Verizon in here. On the other side of the building, we've got big high-speed connections coming in here from, say, Vodafone, British Telecom, AT&T, Orange, and CenturyLink. So this is what you've got coming in. Now, this link could be going back to Japan. This link could be going to Dubai Internet City. This link could be going to Madrid. This link could be going to Panama City, Panama, and this could be New York for Verizon. So we have these little switches in here, and these switches enable us to do what's called the cross connect. So I connect NTT to this switch, and NTT is then connected to Vodafone in this switch. Now, Etisalat is connected to this switch, as is BT. So here's where these were initially coming from before the content delivery networks. And here's how this works. So I've got a user from the Middle East. The user came in, they were coming from Dubai. They came in on their Etisalat. This thing took them to Miami, Florida. From Miami, Florida, they connected to Vodafone, and then they could connect to somebody in England. Anybody realize how expensive these links are coming in? So these links are really expensive. And to go from this link that's say in Tokyo to this link that's say in Dubai Internet City, this could be 10 milliseconds or 15 milliseconds, and these links are expensive to use. So if you're the internet service provider, do you want to use these links for wasted traffic, or do you want to use it for only what matters? Only what matters, right? So what companies do is they then put a caching server in here. I'm going to pick Akamai because it's the largest CDN in the world. So let's say Akamai servers are here. I just picked them at random. So now here's what happens. We've got a user from Etisalat coming from Dubai. Do they hit the Akamai content delivery network and they get access to something that was in England and they don't even have to leave this building because it was cached on this content delivery network? Now, while we're at it, the user in Japan wants to catch something that's from New York City. So they hit this caching thing, and the caching thing stored it from the last time somebody requested it from Verizon. That is the content delivery network and how these things work and the internet meet me rooms. So by doing so, here's what we've truly enabled. We've reduced the load on these wide area network connections. And so we can basically jump off the network right here, get the data here inside of the same building, reducing latency, reducing load on these links, and reducing the load on the servers. And if the request that's coming in is bad, we can drop it right here. Now, this could be Akamai, this could be Cloudflare, this could be AWS CloudFront, this could be Azure, what's the front door? It doesn't matter, but that's the way these work.
All right. I'm going to try and get through these last remaining questions, and then we will have to end for the day. This may or may not be the place for this question, Mike. If you can think of somewhere else to direct them, we got plenty of this. Please explain NAT instance and NAT gateway and their respective use cases.
So all a NAT instance is, it's a combination router that does NAT that's used on a cloud provider to let you go out of the internet and come back. That's it. And that's the only thing you can use it for. Now, you could always take the internet and you could use a firewall, and we've been doing that for 30 years with what they're calling a NAT instance or NAT gateway. Now, what's a NAT instance? It's a made up term from AWS that's a garbage term that's meaningless. It is a router that translates internal addresses to external addresses or one address to another. So if I am company A and I'm using the 10.x address space and I buy company B that's also using the 10.x address space, we can't talk to each other. So I need to use NAT to go from one company to another company to translate the IP addresses so that every address can be unique. And for that, we typically do it on the firewall. I'm sorry, on the routers that are devices that we have. But if you're on the cloud, you don't have access to their routers. So what you do is you get a virtual machine, and then you tell that virtual machine to act as a router and do NAT. Which means when you're running a NAT instance, it's a real thing and you manage it. And you have 100% control over it. When you use a NAT gateway, it's a provider saying, here's our virtual NAT service. We're going to charge you like crazy for it. And trust us, it's just as secure as the real deal that you could use a next generation firewall and an internet gateway. That's what it is. So there's lots of times that you would choose to use one versus another. The NAT gateway might be too expensive if you use it a lot. But the bigger question is what you're using and why you're using it.
All right. All right, so this will be the last question that we've gotten. So it says, expanding on the use of proxy and reverse proxy architectures for routing and load balancing, are there alternative messaging or event-driven solutions such as Redis, Kafka, or other message queues that we could use to handle asynchronous communication, decouple services, or improve fault tolerance? How do these options compare in terms of scalability, latency, and reliability?
Okay, so you're asking me two entirely unrelated things. So you're basically saying, does the cat have a heart and can we drive in a car to get to the destination? So I don't really understand any of the way that you're trying to relate these because we will need to use proxies and load balancing for availability, but we will also have applications that need to send messages from one location to another. So it's not like it's an either or situation. We're going to need both. They're just two completely unrelated technologies to each other.
All right. That is the end of the day. I'll let you give us some closing words, Mike.
Well, I have to say it was really fun spending some time with all of you, kind of getting into cybersecurity. I kind of played a little geeky on the networking side and I didn't do it the way I normally would because I wanted you to see the connections, how the one thing connects to the next thing, which impacts the next thing, which impacts the next thing, which impacts the net thing. And the reason I was so focused on it is that's the thing that goes on interviews. We ask you one and how does it interact with one and another and another. So that's what I wanted to see you have. And I think everybody did a great job today. There were some questions that I hope I was able to ask. I am not like an application architect to look at message buses and message queues, that kind of thing, but my life has been spent in high availability system design, which security is a big part of it, networking, which is a huge kind of component of it, and I'm really honored that you're all here. I saw people in Ghana. I saw people in the Middle East. I saw people in Asia. I saw people all over Central and South America, all over Africa, Europe. So to me, this is kind of a wonder thing that we can all be get together and get here. I'm thrilled you're here, and I look forward to seeing you in the next one. So take care, everyone, and I'll see you soon. Have a great day.